Nothing. What is it? Is it truly nothing, or does it represent something far more profound than mere absence? At first glance, it might seem simple, a void, devoid of substance and meaning. But could this emptiness carry deeper significance, serving as the silent backdrop upon which the drama of existence is painted? Could the concept of nothing be more than just the absence of everything we know? Could it be the very foundation upon which all that exists rests? Imagine for a moment a corner of the universe, one isolated from everything. No stars, no planets, no galaxies, just a quiet, empty space. In this pocket of cosmic isolation, the laws of physics themselves seem to shift, as if the very fabric of reality behaves differently. Here, in this vast emptiness, lies a paradox, a nothingness that seems alive with potential, a nothingness that is, in a strange way, everything. But where did this emptiness come from? What is the origin of nothingness? What secrets does it hold about the universe itself? Join us on a journey through the vast expanse of space, where we'll explore the latest advancements in technology and uncover the hidden mysteries of this elusive concept, nothing. The more we probe, the more we discover that nothing, especially in the context of the universe, is far from simple. At first glance, it may seem like empty space, devoid of matter or energy, but this nothing is anything but. When examined closely, nothing takes on an entirely new, far more complex and intriguing nature. Scientists argue that even the emptiest regions of space, once thought to be completely void of anything, are filled with a chaotic, seething energy. This energy manifests in the form of virtual particles, constantly popping in and out of existence. These particles, born from the very fabric of space, form a fluctuating energy field, suggesting that even the vacuum of space, the so-called nothing, is far from empty. This revelation comes from the groundbreaking principles of quantum mechanics, a theory that describes the behavior of nature at the smallest, most fundamental scales. According to quantum theory, the very idea of nothing, a complete, absolute void, does not exist. Instead, space itself is alive with potential, teeming with fluctuations that create and annihilate particles in an instant. These fleeting particles, though invisible to the naked eye, have measurable effects, influencing everything from the structure of matter to the behavior of light itself. In fact, some of the most groundbreaking theories in cosmology, such as the theory of cosmic inflation, suggest that our entire universe might have originated from this nothingness. According to this theory, the Big Bang, the event that birthed the universe as we know it, could have been the result of a fluctuation in this primordial vacuum. In other words, the universe could have emerged from an infinitesimally small, energy-rich vacuum, a state of nothing bursting into everything. This challenges our understanding of the cosmos, urging us to rethink everything we know about space, time, and the very nature of reality. What this means is that nothing is not just the absence of matter, but rather a dynamic, foundational force. In fact, nothingness may be a key player in the very fabric of the universe. Quantum mechanics reveals that even the empty vacuum of space is teeming with energy, filled with virtual particles that exist in a constant state of flux. In this context, nothing is not merely a void, but a place of infinite potential, a fertile ground where particles emerge and vanish, and where the very laws of physics as we know them are shaped and tested. Yet, this concept of nothingness is still further complicated by the Heisenberg uncertainty principle, a cornerstone of modern physics. This principle suggests that there are fundamental limits to how precisely we can measure certain pairs of physical properties, such as the position and momentum of a particle, simultaneously. In essence, it tells us that the universe is inherently uncertain, that even in a perfect vacuum, there will always be some level of unpredictability. This uncertainty permeates the very idea of nothingness, suggesting that even the emptiest parts of the universe are, in a sense, not truly empty at all. This leads us to a fascinating and paradoxical conclusion. The more we learn about the nature of nothingness, the more we realize that our understanding of it is incomplete. Nothing, in its purest form, may be an abstract, perhaps unreachable concept. The more we investigate, the more we uncover a universe rich with complexity, even in the emptiest corners. The concept of nothingness itself seems to hint at the deep, hidden layers of reality waiting to be explored. The story of nothingness cannot be told without addressing the very beginning of the universe. To understand nothing, we must understand the origins of everything, the Big Bang. Approximately 14 billion years ago, all of the matter and energy that now make up the universe were concentrated into an infinitesimally small point, a singularity of infinite density and zero volume. At that moment, space itself was created, along with time as we know it. Before the Big Bang, the very concepts of space and time did not exist. There was no before because time had yet to begin. This presents a paradox. How can we speak of a time before time? How can we discuss the origins of the universe when the very idea of origin depends on the flow of time itself? To comprehend this, we turn to Albert Einstein's theory of general relativity, which revolutionized our understanding of space and time. According to general relativity, space and time are not separate entities, but are intricately woven into a four-dimensional continuum known as spacetime. This theory implies that before the Big Bang, there was no spacetime, and without spacetime, there could be no time as we experience it. The very fabric of the universe, the stage upon which all events unfold, did not exist in any meaningful sense prior to the Big Bang. Therefore, the origins of the universe challenge our conventional understanding of time, space, and the very nature of reality itself. In this context, the speed of light becomes an essential key to understanding the universe. Light, traveling at an astounding 300,000 kilometers per second, sets a fundamental limit on the speed at which information and matter can travel through space. This speed limit, established by Einstein's theory of relativity, has profound implications for our understanding of the size and age of the universe. Light from distant galaxies takes billions of years to reach us, meaning that when we look at far-off regions of space, we are essentially looking back in time. The constant speed of light serves as a cosmic clock, allowing astronomers to trace the history of the universe from its earliest moments to its current state. Through this lens, we can begin to unravel the mysteries of the cosmos, gaining insight into the state of the universe just moments after the Big Bang. And so as we explore the concept of nothingness, the vast, empty voids of space and the mysterious forces that govern them, we are confronted with the most profound questions about the origins of the universe, the nature of time, and the very meaning of existence itself. What does it mean to truly understand nothing? Perhaps in the end, nothing is not something to be understood, but something to be experienced. A paradoxical void that is anything but empty. A dynamic force that shapes the universe in ways we are only beginning to comprehend. The speed of light is not just a fundamental constant in physics. It serves as the very backbone of our understanding of the cosmos. It defines the boundaries of the observable universe, acting as a cosmic horizon beyond which no information can travel to us, no matter how fast it may be moving. As light travels at a finite speed, its journey is bounded by the age of the universe itself. Thus, anything beyond this limit remains forever out of reach. In essence, the speed of light acts as a timekeeper, a clock of sorts for the universe, telling us how far we can look back in time and the furthest reaches we can comprehend. This constraint doesn't just define the observable universe, it structures the very way we think about the cosmos, shaping our understanding of its origins. Cosmologists, those intrepid explorers of the universe's deepest secrets, face a daunting challenge: understanding the origins of the universe itself. This pursuit is both exhilarating and frustrating, a journey through the unknown, where every discovery raises new questions. But perhaps one of the most significant hurdles they encounter is the limitation imposed by the observable universe. Light, though it travels incredibly fast, has not had enough time to reach us from regions beyond a certain distance due to the finite time since the Big Bang. This creates a cosmic fog, a veil over the early history of the universe that is forever beyond our direct observation. These inaccessible regions remain an eternal mystery, leaving gaps in our knowledge about the universe's infancy. Adding to the complexity of this pursuit is the challenge of interpreting the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang itself. The CMB is a relic of the universe's earliest moments, carrying invaluable information about its birth. Yet, this information is far from straightforward. To decode the subtle fluctuations in this radiation, scientists must employ cutting-edge technology and complex mathematical models, capable of analyzing data at a level of precision that pushes the limits of our current scientific understanding. The CMB offers glimpses into the universe's infancy, but much of its true meaning remains hidden behind a veil of intricacy. Even more perplexing is the presence of dark matter and dark energy, two invisible forces that together make up the majority of the universe's mass and energy. Though we cannot see them directly, their presence is undeniable, their influence felt in the very structure and evolution of the cosmos. These enigmatic entities guide the formation of galaxies, the motion of stars, and the expansion of the universe itself. Yet, despite their profound impact, they continue to evade detection, making them some of the most frustrating and tantalizing subjects of study in modern cosmology. The universe's infancy was marked by extreme conditions, temperatures and energy levels so high that they cannot be recreated in current particle accelerators. As a result, many aspects of the Big Bang and its aftermath are hidden from direct observation. Our only window into these events comes from indirect astrophysical evidence, observations that offer tantalizing clues but no definitive answers. This means that much of our understanding of the universe's birth relies on inferences drawn from the behaviors of distant galaxies, the radiation from ancient stars, and the subtle ripples in spacetime itself. At the heart of modern cosmology lies the Big Bang theory, the idea that the universe began as an infinitely hot and dense point, a singularity, before undergoing an explosive expansion. This theory, which dates back roughly 14 billion years, has been the cornerstone of our understanding of the universe's origin. But the Big Bang, while providing a compelling explanation for the observable characteristics of the universe, the vastness of its expansion, the presence of the cosmic microwave background, also raises profound questions about what came before. The singularity, the point from which the universe is thought to have emerged, is a concept rooted in general relativity. However, under the extreme conditions of the singularity, general relativity breaks down, leaving us with a gap in our understanding of how the universe could have transitioned from nothing to something. Here, quantum theories of gravity offer a tantalizing glimpse into the unknown, suggesting that the concept of a singularity might not even be relevant in the context of the universe as we understand it. Some theories even hint at a pre-Big Bang scenario, suggesting that the universe might have undergone cycles of birth and rebirth, or that the very idea of nothing may be fundamentally different from our conventional understanding. Despite its elegance in explaining many of the observable features of the universe, the Big Bang theory does not provide a comprehensive answer to the most profound question of all. What came before the Big Bang? What, if anything, existed prior to the universe's explosive expansion? As cosmologists continue to explore these deep questions, they are confronted by the limits of both our observational tools and our theoretical frameworks. The mystery of the transition from nothing to something remains one of the most profound and perplexing puzzles at the heart of cosmology, a riddle that continues to challenge our deepest understanding of the universe's origins. This quest for knowledge is far from over. With each discovery, we push the boundaries of what we know, yet the universe remains an elusive and mysterious entity, its true nature hiding behind layers of complexity, vast distances, and impenetrable forces. The speed of light, dark matter, dark energy, and the enigmatic beginnings of the cosmos are just a few of the many puzzles that cosmologists strive to solve, pushing the frontiers of human knowledge further and further into the unknown. The Big Bang theory, the prevailing cosmological model explaining the universe's early development, is underpinned by several key lines of evidence that together form a compelling narrative of our universe's origin. It provides a framework for understanding how the cosmos evolved from a hot, dense state into the vast, expanding universe we observe today. Among these lines of evidence, three foundational observations stand out, each offering a unique piece of the puzzle that is the birth of the universe. First and foremost is the observable expansion of the universe, a critical piece of evidence supporting the Big Bang theory. In the 1920s, astronomer Edwin Hubble made a groundbreaking observation. Galaxies are moving away from us in all directions. This discovery was not just a curious fact, but a revelation that the universe is expanding. The implications were profound. If galaxies are receding from one another, it suggests that the universe was once much smaller, denser, and hotter, a singularity from which the cosmos began its outward expansion. This observation provides a direct link to the idea of a singular beginning for the universe, a key concept of the Big Bang theory. The expansion of the universe is still ongoing, and it implies that if we trace the expansion backward, there must have been an initial point of origin, an explosive moment that set everything in motion. Another pivotal piece of evidence is the discovery of the cosmic microwave background radiation, CMBR, which acts as a relic from the early universe. This faint, pervasive radiation was accidentally discovered in 1965 by Arno Penzias and Robert Wilson, who initially thought they were dealing with an experimental error. However, further investigation revealed that the CMBR is a residual afterglow from the Big Bang, dating back to roughly 380,000 years after the event. During this early period, the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely for the first time. This ancient light has been stretched into microwave wavelengths due to the universe's ongoing expansion, but it provides a snapshot of the universe's state at this critical moment. The CMBR is not just a faint whisper from the past, but a treasure trove of information about the early cosmos. The radiation is remarkably uniform across the sky, with minute fluctuations that offer valuable clues about the universe's structure and the distribution of matter at the time. These slight temperature variations, mapped by satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, reveal the early seeds from which galaxies and other large-scale structures would later form. By studying the CMBR, cosmologists can determine the age of the universe, its overall composition, and its rate of expansion, providing precise constraints on models of its development. The CMBR, in effect, serves as a cosmological Rosetta Stone, decoding the universe's early conditions and refining our understanding of its origins. The third line of evidence supporting the Big Bang theory is the abundance of light elements like hydrogen, helium, and trace amounts of lithium, which were formed during the universe's earliest moments. According to the Big Bang nucleosynthesis model, these elements were forged in the first few minutes after the Big Bang in a process known as nucleosynthesis. In the incredibly hot and dense early universe, protons, neutrons, and electrons combined to form the first atomic nuclei. During the first few minutes, nuclear reactions occurred at an extraordinary pace. Protons and neutrons fused to create deuterium, an isotope of hydrogen, which then fused into helium-3. Some helium-3 nuclei further combined to form helium-4, the second most abundant element in the universe. Tiny amounts of lithium and beryllium were also produced in these early moments. The proportions of these primordial elements, roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium and beryllium, match remarkably well with the predictions of the Big Bang nucleosynthesis model and are consistent with observations made in the most distant ancient galaxies. This agreement between theoretical predictions and observed abundances strengthens the case for the Big Bang theory and offers insight into the conditions that existed during the universe's earliest moments as it began to take shape. In addition to these three pillars of evidence, the Big Bang theory also addresses some of the most profound mysteries in cosmology. One such puzzle is the horizon problem, which refers to the observation that regions of the universe that are extremely distant from one another appear to have the same temperature and density. This is surprising because, according to the speed of light limit, distant regions should not have been able to communicate with one another or share information. Given the vastness of the universe and its age, different regions should display significant variations in temperature and density. The solution to this conundrum lies in the concept of cosmic inflation, a theory proposing that in the moments following the Big Bang, the universe underwent an extraordinary exponential expansion. This period of inflation occurred in an infinitesimally short time span, expanding the universe by a factor of 1 trillion times in a fraction of a second. The rapid expansion stretched out any initial irregularities and differences in temperature and density, leading to the remarkably uniform universe we observe today. This theory not only resolves the horizon problem, but also offers a deeper understanding of how the large-scale structure of the universe emerged. Thus, the Big Bang Theory is supported by a wealth of evidence that paints a coherent and compelling picture of the universe's origins. From the observable expansion of galaxies to the discovery of the CMBR and the primordial abundances of light elements, these pieces of evidence converge to reveal a universe born from an intensely hot and dense state, expanding and evolving over billions of years. Each discovery refines our understanding of the cosmos and brings us closer to answering one of humanity's oldest questions: how did the universe come to be? The Big Bang Theory not only provides a framework for understanding the past, but also guides our exploration of the universe's future, as we continue to unravel the mysteries of space and time. Inflation, a key theory in modern cosmology, offers a solution to one of the most puzzling problems in the universe's early history: the horizon problem. This issue centers on the apparent uniformity of the universe, even in regions that are so far apart that they could not have been in causal contact with each other. According to the inflationary model, however, these distant regions originated from a small, causally connected volume of space in the universe's earliest moments. This rapid expansion effectively smoothed out any variations, ensuring that the vast regions of space we observe today were once linked in a shared early history. Moreover, inflation offers predictions that have been confirmed by observations. One of the most significant predictions is the existence of slight variations in the temperature and density of the cosmic microwave background, CMB, radiation, relics from the universe's infancy. These fluctuations, which reflect the seeds of all large-scale structures in the universe, have been observed by several key instruments, including the Cosmic Background Explorer (COBE), the Wilkinson Microwave Anisotropy Probe (WMAP), and the Planck satellite. These small, subtle differences in the CMB are direct evidence of the quantum fluctuations that occurred in the universe's infancy, when inflation was at its peak. At the heart of this inflationary process are quantum fluctuations, temporary and minuscule changes in the amount of energy at a specific point in space. According to quantum mechanics' uncertainty principle, it's impossible to know both the exact position and momentum of a particle simultaneously. This inherent uncertainty leads to the creation of particle-antiparticle pairs that spontaneously emerge from the vacuum, only to annihilate each other almost immediately. However, these fluctuations do not violate the conservation of energy because they occur over incredibly short timescales. These ephemeral events are not just theoretical, they have real-world consequences, such as the Casimir effect, which demonstrates the physical reality of quantum fluctuations by showing how they generate a measurable force in certain conditions. In the context of the universe's origin, quantum fluctuations are indispensable. During the epoch of cosmic inflation, these minute, transient energy shifts in the inflaton field, an energy field thought to have driven inflation, became stretched across vast distances as space expanded exponentially. These fluctuations in the inflaton field became the seeds for the cosmic structures we see today. The tiny variations in density seeded by quantum fluctuations eventually grew into the galaxies, clusters of galaxies, and large-scale structures that populate the observable universe. Interestingly, some theoretical models go even further, suggesting that the universe itself might have emerged from a quantum fluctuation in a pre-existing space or even in a different universe altogether. While this idea remains speculative, it offers a fascinating glimpse into how quantum mechanics could potentially explain the very origin of the cosmos. This concept underscores how deeply intertwined quantum fluctuations are with both the large-scale structure of the universe and, quite possibly, its very creation. It exemplifies the profound role that quantum mechanics plays in not just shaping the cosmos we observe, but possibly in bringing it into existence. In this framework, quantum fluctuations serve as a bridge between the minuscule world of particles and the grand expanse of the cosmos. Their role is not limited to creating the conditions necessary for the universe's expansion, but could also be integral to the universe's birth. According to quantum theory, the universe may have arisen from what is essentially nothing, in the sense that it could have emerged from a quantum vacuum. This vacuum, however, is far from empty. Instead, it is teeming with virtual particles, pairs of particles and antiparticles that appear, separate, and annihilate each other in an endless cycle. These virtual particles are the cornerstone of quantum field theory and play a pivotal role in theories suggesting that the universe arose from a vacuum state. In the quantum realm, this state of nothingness is not truly devoid of activity. Instead, it is filled with potential energy, constantly fluctuating as virtual particles pop in and out of existence. Though these particles are short-lived, their effects are observable. The Casimir effect, for example, demonstrates how these virtual particles can exert a measurable force between two closely spaced metal plates in a vacuum, a striking real-world manifestation of quantum mechanics. Virtual particles offer a compelling explanation for how the universe could have originated from what seems like nothing. In this view, a particularly significant quantum fluctuation, a disturbance of the right magnitude, could trigger the birth of a universe. This fluctuation would not quickly annihilate itself, but could persist long enough to provide the necessary energy to spark the Big Bang. The Big Bang in this scenario marks the universe's sudden expansion from a singularity, a point of infinite density, to the vast, cool universe we observe today. This idea aligns with the laws of quantum mechanics, which allow for the spontaneous creation of energy and matter from a vacuum, suggesting that the universe could have emerged from a quantum fluctuation without violating the conservation of energy. Beyond the creation of matter and energy, this framework of quantum fluctuations also challenges our understanding of time itself. Models that integrate quantum mechanics with general relativity, such as the Hartle-Hawking state, propose that time itself could have emerged from the quantum state of the universe. In this view, time did not exist in any conventional sense before the Big Bang. Instead, it was born out of the same quantum processes that gave rise to matter and energy, smoothing the transition from an initial quantum vacuum state to a universe filled with the familiar fabric of spacetime. In this context, quantum theory offers a profound shift in how we perceive the origins of the cosmos. Instead of imagining the universe emerging from a singular, timeless event, we are invited to consider a universe that arose from the quantum fluctuations within the vacuum, a transition from nothing to something, where the laws of physics themselves were part of the emerging reality. Virtual particles are central to this concept, offering a mechanism by which the universe could have emerged from the quantum vacuum, filling the role of both the origin and the process that allowed for the formation of the universe as we know it. The idea that the universe could have emerged from a quantum fluctuation challenges our conventional notions of creation. But quantum mechanics provides a compelling framework for understanding how the cosmos may have arisen not from an external source or a singular event, but from the very fabric of the quantum field itself, an ever-present potentiality that governs the universe's most fundamental aspects. It offers a glimpse into a universe far more complex and mysterious than we once imagined, where even the vacuum of space holds the potential for the birth of everything we see around us. Virtual particles lie at the heart of some of the most profound and intricate cosmological theories that attempt to explain the origins of the universe. These theories aim to uncover how the cosmos might have emerged from an almost incomprehensible state of nothing, and they highlight the deep intersections between the enigmatic realm of quantum mechanics and the vast, expansive field of cosmology. At the core of this exploration is Heisenberg's uncertainty principle, a fundamental pillar of quantum mechanics. This principle posits a strikingly counterintuitive idea. There is a limit to how precisely we can know certain pairs of physical properties, like position and momentum, at the same time. This seemingly simple concept has far-reaching consequences, particularly when applied to the early universe. The uncertainty principle provides a framework for understanding that, at extremely small scales and incredibly high energies, such as those that would have existed at the dawn of the universe, predictability and determinism are no longer feasible. The universe's very early state was shaped by a realm of uncertainty, where the laws governing space and time were subject to constant fluctuations. These quantum fluctuations, governed by the uncertainty principle, introduce an inherent instability in the universe's primordial conditions. These fluctuations could have been the catalysts for the spontaneous creation of particles seemingly out of nothing. In this view, the very energy that propelled the early expansion of the universe could have emerged from what is known as the quantum vacuum, an almost paradoxical state where nothing can give rise to something. In essence, these fluctuations form the bedrock of ideas that challenge our conventional understanding of the universe's birth. Instead of a neatly defined singular beginning, the uncertainty principle suggests that there may not have been a singular point of infinite density and temperature, the so-called singularity, commonly associated with the Big Bang. Rather, the uncertainty principle implies that the concept of a singular, well-defined starting point for space and time might be fundamentally flawed. Instead of an exact, pinpointed origin, there could have been a more fuzzy, imprecise beginning. This fuzziness, this indeterminacy, suggests that the universe's inception could have involved a pre-Big Bang state, one where our familiar notions of time and space simply ceased to apply. The conditions of the universe during this moment would have been governed by quantum effects that remain largely mysterious, offering new pathways for theories that move beyond the classical Big Bang model. Thus, the uncertainty principle does more than add to the mystery of the universe's origins. It introduces an entirely new way of thinking about the cosmos, one where the very foundations of space and time are seen not as stable, unchanging entities, but as malleable, uncertain constructs subject to the whims of quantum fluctuations. In this light, we begin to understand that the universe's birth was not a deterministic event, but rather an inherently unpredictable process. This opens up possibilities for understanding the cosmos in ways grounded in the core principles of quantum mechanics, where uncertainty and probability reign. Quantum mechanics itself is a groundbreaking theory that describes the physical world at the atomic and subatomic levels. Its implications stretch far beyond the confines of particle physics and have forced us to reconsider the very nature of space, time, and the universe itself. In classical physics, space and time are often viewed as separate, fixed entities, a stage upon which events unfold in a linear, predictable manner. However, quantum mechanics introduces a paradigm-shifting perspective, suggesting that at the smallest scales, space and time blur together. The rigid, mechanistic view of the universe is replaced with a far more fluid and interconnected system of probabilities. One of the most mind-bending concepts that arise from quantum mechanics is the phenomenon of quantum entanglement. In this extraordinary state, particles become so deeply connected that the state of one particle can instantly influence the state of another, regardless of the distance between them. This defies our classical understanding of space as the mere distance between 2 points and time as a linear, forward-moving progression. Quantum entanglement suggests a kind of deep interconnectedness that transcends the conventional boundaries of space and time. At the earliest moments of the universe, during the Planck epoch, which lasted for the first 10 to the power of -43 seconds after the Big Bang, the very fabric of space and time, as we know them, did not exist in any meaningful form. Instead, the universe was in a state of extreme density and temperature, where the laws of physics, as we understand them, cease to be applicable. In this moment, classical physics fails us, and the universe's most fundamental properties become indistinguishable from one another, governed by quantum effects that we are only beginning to understand. This era of the universe's birth challenges our most deeply ingrained Newtonian views of reality. The classical view of space as an immutable backdrop to events and time as a smooth, linear progression is shattered. Instead, these concepts emerge from a state of extreme quantum uncertainty, where even the most fundamental aspects of reality were in a state of constant flux. The idea that space and time themselves are products of quantum phenomena forces us to rethink not only the origins of the universe, but also the very structure of reality itself. In this framework, the theory of cosmic inflation offers a key insight into the universe's rapid expansion just after the Big Bang. This theory proposes that in the first moments of the universe's existence, around 10 to the power of -36 seconds after the Big Bang, the universe expanded at an exponentially faster rate than anything we can comprehend. This rapid expansion helps solve several of the deepest puzzles in cosmology, such as the uniformity of the universe. Without inflation, it would be difficult to explain why distant regions of the universe have the same temperature and density, as they could not have been in contact long enough to equilibrate. Furthermore, the inflationary theory accounts for the large-scale structure of the universe. The brief but intense period of inflation stretched out tiny quantum fluctuations in the early universe, which later gave rise to the galaxies and clusters of galaxies that we observe today. These fluctuations, laid down during the inflationary epoch, form the seeds for the cosmic structures that would later emerge. In sum, the interplay between quantum mechanics and cosmology offers a new and profound lens through which to view the universe's birth. The uncertainty principle, quantum fluctuations, and inflationary models all contribute to a radically different understanding of the cosmos, one in which uncertainty, imperfection, and unpredictability were not anomalies, but fundamental features of the universe's very creation. This perspective invites us to rethink everything we know about space, time, and the origins of everything we see. Cosmic inflation, a theory that radically reshaped our understanding of the universe's origins, offers a profound and compelling explanation for many of the universe's most intriguing features. It not only provides an elegant solution to long-standing cosmological puzzles, but it also closely aligns with a wealth of observational evidence, forming a critical part of the cosmological framework. One of its most significant predictions is the flatness of the universe, a striking feature that mirrors observations of the cosmic microwave background radiation. This theory, in essence, redefines our understanding of the universe's birth and development, weaving together disparate threads of scientific inquiry into a cohesive and unified narrative. At the heart of cosmic inflation is its solution to the flatness problem in cosmology, a question that had confounded scientists for decades. Why does the universe appear so geometrically flat? In other words, why is the total energy density of the universe so incredibly close to the critical value needed to achieve a perfectly flat universe? This question becomes even more perplexing when one considers the natural expectation that the universe, given its vastness and complexity, should deviate significantly from flatness, unless its initial conditions were fine-tuned to an almost impossible degree. Before the concept of cosmic inflation was introduced, this enigma presented a serious challenge to cosmological theory. Conventional models struggled to account for the universe's apparent flatness, suggesting that the conditions at the dawn of the cosmos must have been uniquely tailored. However, cosmic inflation offered a bold and revolutionary resolution. According to this theory, an extraordinarily brief but immensely rapid expansion of the universe occurred just moments after the Big Bang. During this phase, any initial curvature of space, whether it was slightly curved or even highly distorted, was stretched to such an enormous extent that the universe appeared flat, not only to our eyes but on scales smaller than the observable universe itself. This process is reminiscent of how the Earth, despite being a massive sphere, appears flat to someone standing in one location. The curvature of the Earth is so subtle over short distances that it's virtually undetectable. Similarly, the inflationary expansion stretched the very fabric of the universe, making any pre-existing curvature so slight that it became imperceptible across the observable universe. As a result, the universe's geometry seemed to be perfectly flat, and its density was driven incredibly close to the critical value required for flatness. This elegant solution, proposed by cosmic inflation, does away with the need for finely tuned initial conditions, making a flat universe a natural consequence of this rapid expansion. Yet, cosmic inflation is not merely a theoretical construct. It is grounded in a solid foundation of observational evidence that lends it significant credibility. One of the most powerful pieces of evidence supporting the theory comes from the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang. This radiation is nearly uniform, yet it contains tiny temperature fluctuations that hold crucial information about the early universe. These fluctuations reflect variations in the density of matter that existed in the universe's infancy, And it is these very fluctuations that would eventually evolve into the galaxies and vast cosmic structures we observe today. Satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft have mapped these fluctuations with remarkable precision. Their findings match the predictions made by cosmic inflation theories almost perfectly, further validating the model and providing a direct link between the inflationary expansion and the observable universe. The patterns of temperature fluctuations in the CMB provide a snapshot of the universe when it was just a few 100,000 years old, offering a glimpse into the cosmic past that is astonishingly consistent with the inflationary model. In addition to the CMB, the large-scale structure of the universe, such as the distribution of galaxies and galaxy clusters across vast stretches of space, also offers compelling evidence for cosmic inflation. The observed patterns in the placement of galaxies can be traced back to tiny quantum fluctuations in the very early universe. These fluctuations, magnified during the rapid expansion of inflation, laid the foundation for the large-scale structures we observe today. The alignment of these structures with the predictions of inflationary models strengthens the argument that the universe's formation is intricately linked to the inflationary epoch. Another significant layer of evidence comes from the flatness of the universe, confirmed through precise measurements of the CMB's anisotropies. A flat universe, as predicted by cosmic inflation, is a direct consequence of the rapid expansion that occurred during the inflationary period. This confirmation of flatness through observation further supports the theory, suggesting that the universe's geometry was shaped by processes that are both consistent with the predictions of inflation and observable in the data we now possess. Perhaps the most recent and groundbreaking evidence comes from the discovery of B-mode polarization patterns in the CMB, detected by experiments such as BICEP-2. These patterns are thought to be the imprint of gravitational waves produced during the inflationary epoch, a key prediction of inflationary theory. While interpretations of these findings are still under active scrutiny, their potential to confirm the existence of gravitational waves from the early universe adds an exciting new dimension to our understanding of cosmic inflation. If confirmed, this discovery would provide a direct observational signature of the inflationary period, offering unparalleled insight into the universe's birth. Taken together, these pieces of evidence, the temperature fluctuations in the CMB, the large-scale structure of the universe, the confirmation of the universe's flatness, and the possible detection of gravitational waves, form a robust and compelling case for cosmic inflation. The theory provides a coherent and comprehensive explanation for the universe's initial conditions, structure, and evolution, and it aligns remarkably well with the empirical data collected from a variety of observational tools. Cosmic inflation has revolutionized our view of the universe, transforming what was once an enigmatic and mysterious set of observations into a coherent and predictive theory. It has not only solved the flatness problem, but has also provided a framework for understanding the universe's deep origins, its vast scale, and its ongoing evolution. As our observational tools become more sophisticated and our understanding of the cosmos continues to evolve, the theory of cosmic inflation will likely remain a cornerstone of cosmological research, offering new insights into the very fabric of the universe. In the intricate dance of the cosmos, one of the most profound relics from the universe's infancy is the cosmic microwave background, CMB, radiation. Often regarded as the afterglow of the Big Bang, the CMB permeates the entire universe, offering us a glimpse into a time when the cosmos was still a hot, dense soup of particles and radiation. However, it's not just the uniform nature of this radiation that holds significance. Rather, it's the subtle fluctuations or anisotropies within this backdrop that serve as key indicators of the universe's early development. These minute variations in the CMB provide a treasure trove of information, helping scientists understand the birth of our universe, the intricate processes that unfolded during its earliest moments, and the forces that have shaped it over billions of years. At the heart of these fluctuations are quantum variations, microscopic ripples in the very fabric of spacetime itself. In the first fraction of a second after the Big Bang, these quantum fluctuations would have been stretched and magnified to cosmic proportions by the phenomenon known as cosmic inflation. This rapid expansion, occurring at unimaginable speeds, turned these tiny subatomic irregularities into larger regions of slightly differing density, with some areas being just a bit more crowded than others. Over time, these density variations would act as the seeds from which the larger structures of the universe, such as galaxies and galaxy clusters, would eventually form. As the universe aged, regions with slightly higher matter density became the focal points for the gravitational collapse of gas and dust, paving the way for the formation of stars and galaxies. These fluctuations, captured in the CMB, serve as a snapshot of the universe when it was only about 380,000 years old. At this early stage, the cosmos had cooled enough for atoms to form, allowing photons to travel freely through space, marking the moment when the universe transitioned from a hot, opaque plasma into the transparent space we observe today. The imprints of these primordial fluctuations left behind in the CMB have been meticulously studied by a number of space-based observatories, including the WMAP and Planck satellites. The data collected from these missions have revealed a detailed map of the anisotropies present in the CMB, providing us with a window into the universe's earliest moments. One of the most remarkable insights gained from these observations is the confirmation of the predictions made by inflationary models of the universe. For example, inflation theory predicts a scale-invariant spectrum of fluctuations, a pattern where the distribution of these fluctuations remains constant across different spatial scales. This idea that the tiny quantum irregularities that arose from inflation would manifest themselves in a uniform pattern across vast stretches of space has been confirmed with high precision by measurements of the CMB. These findings bolster the view that the fluctuations we see in the CMB were indeed seeded by quantum fluctuations during the inflationary epoch. Additionally, the angular size of the first peak in the CMB power spectrum offers strong evidence for a flat universe, another key prediction of inflationary theory. A flat universe suggests that on the largest scales, the geometry of space is neither positively nor negatively curved, but rather it follows the rules of Euclidean geometry. This idea, once purely theoretical, has now been strongly supported by observational data from the CMB and in further validating the inflationary model. The intricate details of the variations in the CMB, along with their remarkable alignment with inflationary predictions, provide compelling evidence for the theory of cosmic inflation, offering us an unprecedented understanding of the universe's birth and the dynamics that led to the formation of the structures we observe today. Yet, despite the immense progress in our understanding of the universe, there remain many mysteries. One of the most significant of these is dark matter. Invisible to our telescopes, dark matter does not emit, absorb, or reflect light, making it extraordinarily difficult to detect through traditional electromagnetic means. Nevertheless, its presence is undeniable, as its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos are profound. In fact, dark matter is thought to account for approximately 85% of all matter in the universe, with only a small fraction of matter being visible to our instruments. Dark matter's elusive nature has intrigued scientists for decades, but despite being undetectable through electromagnetic radiation, its existence is inferred from its gravitational influence. In the early universe, dark matter played an essential role in shaping the cosmos. In the first moments following the Big Bang, the universe was a hot, dense plasma composed of photons, electrons, and protons. While this plasma was dense, it was not perfectly uniform. There were tiny fluctuations in its density, slight variations in the distribution of matter and energy across space. However, dark matter, unaffected by electromagnetic forces, interacted primarily through gravity. This allowed it to clump together in regions of slightly higher density, forming the first gravitational wells in the universe. These clumps of dark matter would go on to influence the formation of the universe's first structures. As the universe expanded and cooled, these clumps of dark matter and ordinary matter began to interact, with the dark matter providing the gravitational scaffolding necessary for the formation of galaxies and clusters of galaxies. Without dark matter's gravitational influence, the gas and dust in the universe would not have been able to condense and form stars and galaxies as quickly as they did. In essence, dark matter was a vital ingredient in breaking the symmetry of the early universe, creating the conditions that allowed for the formation of the rich and complex structure we observe today. Without dark matter, the universe would be a vastly different place. Its role in the early cosmos was pivotal in the formation of the large-scale structures, galaxies, galaxy clusters, and the intricate cosmic web that define the universe today. The study of dark matter, along with the analysis of the CMB, provides us with key insights into the processes that have shaped the universe, allowing us to trace the history of the cosmos from its earliest moments to the present day. Through these cosmic revelations, we begin to piece together the grand narrative of the universe's evolution, uncovering the forces and mechanisms that have shaped the cosmos over billions of years. From the quantum fluctuations that set the stage for cosmic inflation, to the invisible hand of dark matter that sculpted the structures of the universe, our understanding of the cosmos continues to evolve, offering a deeper and more nuanced understanding of the universe's origin, its present state, and its future. The universe is a vast and mysterious place, and the more we learn about it, the more we realize how much there is left to understand. The behavior of galaxies and galaxy clusters, for instance, presents a series of puzzling patterns and velocities that defy explanation when only the gravitational influence of a visible matter is considered. These phenomena hint at something unseen, something powerful, and something that has shaped the cosmos from the very beginning: dark matter. Although it cannot be directly observed, dark matter's gravitational effects are evident throughout the universe, shaping the dynamics of galaxies and clusters in ways that would be impossible without it. Yet, the puzzle doesn't end with dark matter. There is another mysterious force that governs the universe's expansion: dark energy. Unlike dark matter, which binds galaxies together through gravitational attraction, dark energy has the opposite effect. It exerts a force that pushes galaxies apart, causing the universe to expand at an accelerating rate. This force, which makes up roughly 70% of the universe's total energy content, is both ubiquitous and enigmatic. Despite its dominance, the true nature of dark energy remains one of the most profound and unresolved questions in modern astrophysics. The discovery of dark energy traces back to the late 1990s, when astronomers made an astonishing observation. Not only was the universe expanding, but the rate at which it was expanding was increasing over time. This revelation completely upended previous assumptions. For decades, scientists had believed that the gravitational pull of matter would gradually slow down the expansion of the universe. Instead, the opposite was happening. The universe's expansion was accelerating, and this acceleration could not be explained by the gravitational pull of visible matter alone. Dark energy is thought to exert this acceleration through its unique property, negative pressure. According to Einstein's theory of general relativity, pressure, like mass and energy, contributes to the gravitational potential of a system. While matter exerts a gravitational pull that slows down the expansion, dark energy pushes against that force, accelerating the expansion instead. This acceleration is uniform across the universe, acting equally on every part of the cosmos, and has a profound effect on the future evolution of the universe. The true nature of dark energy remains a tantalizing mystery. Some theories suggest it could be a cosmological constant, an energy inherent to space itself, while others propose that it might be the result of fields or particles not yet discovered by the standard model of physics. Regardless of its precise nature, understanding dark energy is critical to our comprehension of the universe's past, present, and future. It plays a crucial role in determining the ultimate fate of the cosmos, shaping its long-term evolution in ways that are still not fully understood. In traditional physics, nothing was once thought to be simply an absolute void, an emptiness devoid of matter, energy, or radiation. However, the advent of quantum field theory and our deeper understanding of the quantum vacuum have radically transformed this conception. In the quantum view, the vacuum is far from empty. Instead, it is a dynamic state, filled with energy and potential. Virtual particles constantly flicker in and out of existence due to quantum fluctuations. These particles cannot be observed directly, but their presence can be inferred through their indirect effects, such as the Casimir effect, which provides evidence for their transient existence. This new understanding of nothing as a quantum vacuum, teeming with activity and potential, has profound implications for cosmology. One of the most intriguing hypotheses is that the entire universe might have emerged from a quantum fluctuation in this primordial vacuum. This small, seemingly insignificant fluctuation could have been magnified by a process known as cosmic inflation, rapidly expanding it into the vast and complex universe that we observe today. Thus, the cosmos is far more complex and dynamic than once imagined. Dark matter and dark energy, forces that cannot be directly seen but whose effects are clearly observable, shape the universe in profound ways. As we strive to understand these forces, we confront some of the deepest mysteries of existence, from the origins of the universe itself to its ultimate fate. Each discovery adds another layer to the grand cosmic puzzle, and the quest to uncover the true nature of the universe is far from over. The more we explore, the more we realize how much there is still left to learn, and the more we understand how interconnected everything in the universe truly is. This challenge presents more than just a shift in our concept of nothingness. It forces us to reconsider the very nature of creation and existence itself. At the heart of this cosmic puzzle lies the quantum vacuum, a region of nothing that is anything but empty. Instead, it is a seething, bubbling cauldron of potential, an ever-present undercurrent that forms the very foundation of reality itself. This is no longer an abstract concept. It is a dynamic, active force that challenges our fundamental understanding of the universe. The quantum vacuum is far from the serene, empty void that ancient philosophers once envisioned. Rather, it is a state filled with untapped energy and potential, where particles spontaneously appear and vanish in brief, fleeting moments, a phenomenon called quantum fluctuation. This energy, hidden in plain sight, could be deeply connected to some of the most profound mysteries in modern cosmology. For instance, the enigmatic force of dark energy, responsible for the accelerated expansion of the universe, may be intrinsically linked to the quantum vacuum. In the vast expanse of the cosmos, where galaxies drift apart faster than ever, it is the quantum vacuum's energy that could be propelling this expansion, defying all expectations, and urging us to rethink everything we thought we knew about space, time, and gravity. In the grand scope of cosmology, the nature of nothing has evolved into a paradoxical concept, one where the void is anything but void. It is now a bubbling brew of potentiality, a state pregnant with possibilities that extend far beyond the limits of our current understanding. As science delves deeper into this strange realm, our perceptions of existence itself are being continually reshaped, forcing us to challenge our most basic assumptions about reality. However, the puzzle deepens when we turn our gaze toward the most elusive and mysterious components of the universe: dark matter and dark energy. These two phenomena, which together make up nearly 95% of the universe's total mass energy content, remain as enigmatic as ever, defying all attempts at comprehension. While ordinary or baryonic matter, the stuff of stars, planets, and galaxies, constitutes only 5% of the universe, dark matter and dark energy dominate the cosmos in ways we are only beginning to grasp. Despite their profound influence, they remain invisible and undetectable through traditional means. Dark matter, for instance, cannot be observed directly because it does not interact with electromagnetic forces. This means it doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Instead, dark matter's existence is inferred through its gravitational effect on visible matter. It bends light, alters the motion of galaxies, and has left a subtle imprint on the cosmic microwave background radiation, the afterglow of the Big Bang. Its presence is essential to our current models of the universe, yet its precise nature remains unknown. Without acknowledging dark matter, we cannot fully comprehend the structure or evolution of the cosmos. It represents an unseen mass that shapes everything around us, challenging us to reconsider our fundamental understanding of gravity and the cosmos itself. Dark energy, on the other hand, is an even greater mystery. This unknown force is responsible for the accelerated expansion of the universe, counteracting the gravitational pull that should, in theory, slow down this expansion. Its very existence raises profound questions about the nature of space itself, casting doubt on Einstein's theory of general relativity. A force working against gravity seems to defy everything we thought we knew about how the universe operates. But what exactly is dark energy? Where does it come from? And how does it influence the fate of the cosmos? The origin and nature of dark energy remain deeply mysterious. Some theories suggest that it could be a property of the vacuum of space itself, an intrinsic energy that permeates all of space and drives its expansion. Others propose that it could be tied to quantum fields, hidden forces that govern the subatomic world. Regardless of its origin, dark energy presents a profound challenge to our understanding of the universe, pushing the limits of theoretical physics and cosmology. Together, dark matter and dark energy form the crux of a cosmic conundrum that challenges the foundations of our knowledge about the universe's origins and its ultimate fate. These elusive components not only complicate the makeup of the cosmos, but also invite us to reevaluate our traditional cosmological models. As science advances, these mysteries push the boundaries of our knowledge, compelling us to develop new frameworks that can more accurately describe the inception, then evolution, and eventual destiny of the universe. In many ways, they demand that we broaden our understanding far beyond the visible into the shadowy realms of reality that govern the structure and future of the cosmos itself. Another fascinating aspect of the universe's deep mysteries is the role played by neutrinos, particles that, despite their ghostly nature, are key to unlocking the secrets of the early universe. Often referred to as ghost particles because they interact so weakly with other forms of matter, neutrinos are incredibly difficult to detect. These nearly massless particles only interact through the weak nuclear force and gravity, making them elusive and nearly invisible. Yet despite their shyness, neutrinos carry crucial information about the universe's infancy and its evolution in the moments after the Big Bang. In the first few seconds following the Big Bang, the universe was an incredibly hot and dense mixture of particles. Neutrinos were part of this primordial soup, but they decoupled from the rest of the matter when the universe was just 1 second old. Since then, they have traveled virtually unimpeded through space, carrying with them a snapshot of the conditions that prevailed at that time. These primordial neutrinos are the universe's earliest messengers, offering us a unique glimpse into the processes and conditions of the cosmos at its birth. Because neutrinos interact so weakly with matter, they have avoided the complex processes that later led to the formation of atoms, stars, and galaxies. This means they retain a record of the universe at its earliest, most primal stages. By studying neutrinos, scientists hope to unlock new insights into the universe's formative moments, allowing us to piece together the puzzle of how it evolved from a hot, dense state to the vast, complex structure we observe today. The discovery that neutrinos have mass only adds to their intrigue. This finding suggests that neutrinos may play a more significant role in the universe's evolution than previously thought, potentially shedding light on the mysterious forces that govern the cosmos. Together, these phenomena, dark matter, dark energy, and neutrinos, represent some of the most profound mysteries of the universe. They demand that we rethink the very foundations of cosmology and physics, urging us to develop new models and theories that can better explain the complexities of the universe's origins, structure, and destiny. As we continue to explore these deep cosmic questions, one thing becomes clear. The universe is far more mysterious, intricate, and beautiful than we could ever have imagined. The more we learn, the more we realize just how much we have yet to discover. However minuscule, the role of neutrinos in the cosmos carries profound implications that resonate throughout the entire field of cosmology. These subatomic particles, once considered nearly inconsequential, are now understood to play a pivotal role in the universe's grand design. Their presence subtly yet significantly contributes to the total mass of the universe, influencing the very gravitational dynamics that shape its expansion and evolution. In a universe of unimaginable vastness, where galaxies, stars, and black holes dominate our perceptions, neutrinos might seem inconspicuous. Yet, their interaction with gravitational forces suggests that they impact the large-scale structure of the cosmos in ways we are only beginning to grasp. Neutrinos might even have a hand in the formation of cosmic structures, such as galaxy clusters. And by studying these elusive particles, scientists are uncovering new insights into the processes that govern the evolution of the universe itself. In essence, neutrinos provide a unique lens through which we peer into the infancy of the cosmos. They hold the potential to reveal clues about the primordial conditions that existed just after the Big Bang, shedding light on the fundamental processes that gave birth to the universe as we know it. Despite their ghostly nature, the study of neutrinos is integral to unlocking the mysteries of the cosmos, allowing scientists to refine models of cosmic evolution and better understand the forces shaping the universe's vast, interconnected web. The study of neutrinos, in turn, underscores a crucial intersection between the realms of particle physics and cosmology, two disciplines that, when combined, offer a deeper understanding of the universe's structure and its ongoing expansion. Neutrinos are not just particles, they are messengers from the earliest moments of the universe, and their study can transform our comprehension of the cosmos itself. Parallel to these discoveries, particle accelerators like the Large Hadron Collider, LHC, have taken on an even more crucial role in simulating the high-energy environments that prevailed shortly after the Big Bang. These state-of-the-art machines recreate the conditions of the early universe by accelerating protons or lead ions to nearly the speed of light before colliding them in a controlled environment. The temperatures and energy densities generated during these collisions mirror the extreme conditions that existed during the birth of the universe, allowing scientists to recreate and study these cosmic phenomena on a much smaller scale. In these experimental settings, brief but intense fireballs are created, reaching temperatures and energy levels that are virtually impossible to achieve on Earth. This creates a momentary glimpse into the early universe, where fundamental forces, which are usually distinct and separate in our everyday reality, began to unify. In this ultra-high energy environment, particles that are typically stable in our current low-energy universe can suddenly emerge, decay, and interact in ways never before observed. Here, in this primordial soup, exotic particles and states of matter, such as the quark-gluon plasma, begin to take shape. The quark-gluon plasma is a state of matter believed to have existed just moments after the Big Bang, when quarks and gluons, which are normally confined within protons and neutrons, were free to move independently. Studying this form of matter in the lab provides researchers with invaluable insights into the forces and particles that govern the universe. It offers a unique window into the fundamental building blocks of nature, shedding light on the very forces that would go on to shape the universe's evolution. Through these accelerator experiments, scientists have been able to confirm the existence of the Higgs boson, once a theoretical concept, offering a crucial piece of the puzzle that explains why particles have mass. By simulating the conditions that existed shortly after the Big Bang, particle accelerators do not only advance our understanding of particle physics, but also offer a tangible connection to the early universe. These experiments are vital in testing and refining theoretical models of the universe's birth and evolution, providing critical evidence for how the universe evolved from a hot, dense singularity to the vast and intricate cosmos we observe today. As particle accelerators bridge the gap between particle physics and cosmology, they allow scientists to test hypotheses about the very origins of the universe. From its fundamental constituents to the forces that drive its evolution, these experiments provide invaluable information on the birth, structure, and ultimate fate of the cosmos. The LHC in particular offers insights that could reshape our understanding of the universe's deepest mysteries. In an even more groundbreaking development, the discovery of gravitational waves has opened a new frontier in cosmology and observational astronomy. These ripples in the fabric of spacetime, first predicted by Albert Einstein in 1916, are generated by some of the most energetic and violent events in the universe. Colliding black holes, merging neutron stars, and other cataclysmic phenomena create these waves, which travel through space carrying vital information about the sources of these cosmic events. The detection of gravitational waves, achieved a century after Einstein's prediction by the LIGO and Virgo collaborations, represents a watershed moment in our ability to observe and understand the universe. Unlike electromagnetic radiation, such as light, which can be scattered, absorbed, or distorted as it travels through space, gravitational waves pass through matter with little to no obstruction. This characteristic makes them an ideal means for studying the earliest moments of the universe, including the Big Bang and the period of rapid inflation that followed. Gravitational waves offer a pristine, unaltered signal from some of the most energetic processes in the cosmos. They carry with them information from the very infancy of the universe, providing a rare and direct view of phenomena that cannot be observed through traditional means. Furthermore, these waves offer a powerful tool for testing the validity of general relativity in extreme environments, such as the interiors of black holes or the chaotic aftermath of neutron star collisions. The study of gravitational waves could reveal new and unknown aspects of fundamental physics, challenging existing models, and offering clues to physics beyond our current understanding. By probing these extreme conditions, scientists may uncover new layers of knowledge about the very nature of gravity, spacetime, and the universe's origins. The potential for discovery is vast, and gravitational waves have become an essential tool in the ongoing effort to decode the universe's deepest secrets. In conclusion, the fields of particle physics and cosmology are increasingly intertwined, with each discovery in one field shedding light on the other. From the mysterious neutrinos that influence cosmic structure, to the unyielding waves of gravitational energy that pass through the fabric of spacetime, these phenomena offer profound insights into the nature of the universe. As we continue to push the boundaries of human knowledge, these revelations will undoubtedly help us understand not only the universe's past, but also its future. Gravitational waves, those ripples in space-time caused by some of the universe's most violent and energetic events, have already begun to reshape our understanding of the cosmos in profound ways. The detection of these waves from the merger of binary neutron stars, for instance, has not only confirmed a major prediction of Einstein's theory of general relativity, but has also provided surprising new insights into the origins of heavy elements like gold and platinum. This groundbreaking observation lends strong support to the theory that such elements are created in extreme, neutron-rich environments that are capable of producing some of the universe's heaviest and rarest substances. As the field of gravitational wave astronomy continues to evolve, the implications for cosmology become even more expansive. One of the most intriguing possibilities is that gravitational waves could help solve some of the long-standing puzzles that have stymied cosmologists for decades, particularly the precise measurement of the universe's expansion rate. This rate, known as the Hubble constant, has long been a subject of intense debate, with different methods of measuring it yielding slightly different results. By utilizing the consistent and well-understood properties of gravitational waves, scientists hope to calibrate a new standard for distance measurement across the universe, acting as cosmic rulers, so to speak. This would allow for far more accurate measurements than what traditional methods have been able to provide. However, these waves aren't just useful for measuring distances. They also provide a unique opportunity to probe the universe's most energetic and enigmatic phenomena. By studying the sources of these waves, which range from the mergers of black holes to the violent collisions of neutron stars, we gain unprecedented access to the most extreme conditions in the universe. This is helping to refine our models of both the early universe and the fundamental laws of physics that govern it. More than just verifying Einstein's theory, gravitational wave astronomy allows us to challenge the very limits of our understanding, forcing us to rethink what we know about the cosmos and even the laws that seem to govern it. Yet, while these advancements are exciting, they also highlight the limitations of our current cosmological models. The lambda cold dark matter LILCDM model, which has been remarkably successful at describing large-scale phenomena such as the distribution of galaxies and the cosmic microwave background radiation, still faces several significant challenges. At the heart of these challenges lies the mystery of dark matter and dark energy, two of the universe's most elusive components. Together, they make up about 95% of the total mass energy content of the cosmos. Despite their overwhelming presence, the exact nature of dark matter and dark energy remains unknown, creating a vast gap in our understanding of the universe's composition. This gap is a fundamental problem that limits our ability to fully grasp how the universe works on both small and large scales. Another central issue is the horizon problem. Although the inflationary model of the early universe attempts to address this conundrum by proposing a period of rapid expansion that would allow distant regions of the universe to be in causal contact with each other, this theory is far from settled. The exact mechanisms behind this inflationary period are still debated, and the search for alternative models of the universe's early rapid expansion remains one of the most hotly contested areas of theoretical research. Furthermore, the discrepancies in the measurements of the Hubble constant only add to the sense that our current cosmological models may be incomplete. Different methods of calculating the universe's expansion rate continue to yield values that don't quite align with one another. This suggests that there may be hidden aspects of the universe, perhaps new physics that we have yet to discover. On a more localized scale, the LCDM model also struggles to accurately predict certain phenomena, such as the formation and distribution of galaxies. One particularly perplexing issue is the missing satellite problem. This problem arises from the fact that simulations of dark matter predict many more small satellite galaxies surrounding large galaxies like the Milky Way than are actually observed. This discrepancy suggests that there may be something about the nature of dark matter or galaxy formation that we have yet to fully understand. In summary, while the detection of gravitational waves represents a tremendous leap forward in our ability to explore the universe, it also underscores the gaps and mysteries that remain within our current understanding of the cosmos. Gravitational waves provide a new tool, one that promises to open windows into previously inaccessible regions of space and time. However, as they reveal new layers of the universe's workings, they also illuminate the limits of our existing models, pushing us to refine or even rewrite our theories about the cosmos. The future of cosmology may very well hinge on how we integrate these new insights, using them to test the boundaries of known physics and address the unresolved questions that continue to shape our understanding of the universe. The integration of quantum mechanics with general relativity remains one of the most profound challenges in modern physics. Our current understanding of the universe relies on two dominant theories: general relativity, which describes the behavior of massive objects like planets and stars, and quantum mechanics, which governs the behavior of particles at incredibly small scales. However, these two frameworks are fundamentally incompatible. General relativity does not account for quantum effects, while quantum mechanics struggles to address gravitational phenomena on a cosmic scale. This divide presents a significant obstacle to a unified theory of quantum gravity, which is essential for understanding the true nature of the universe across all scales, from the infinitesimally small to the cosmologically large. The need for such a theory is especially pressing when we consider the universe's earliest moments, particularly during the Planck epoch, an incredibly brief yet crucial period following the Big Bang. During this time, the universe was not only smaller than an atom, but also incomprehensibly dense, meaning that both quantum mechanical effects and gravitational forces were acting simultaneously. To fully grasp the universe's behavior during this epoch, a quantum theory of gravity is required, but such a theory remains elusive, despite years of theoretical work and experimentation. Even though our cosmological models, based predominantly on general relativity, have been remarkably successful in explaining numerous astronomical phenomena, they also highlight the gaps in our understanding. The current models, while they provide a powerful framework for understanding the expansion of the universe, dark matter, and the cosmic microwave background radiation, are incomplete. This incomplete picture underscores the necessity of further theoretical and observational advancements. Only through continued exploration and refinement of our models can we hope to address these deep, fundamental questions and move closer to a more complete understanding of the universe. One of the most critical tools for estimating the age of the universe is the observation of the cosmic microwave background, CMB, radiation. The CMB is often described as the afterglow of the Big Bang, the faint residual heat left over from the early universe. This radiation provides a snapshot of the cosmos when it was only about 380,000 years old, offering scientists a glimpse into the conditions of the universe during its infancy. By analyzing the temperature fluctuations in the CMB, scientists can infer vital parameters about the expansion of the universe, such as its density, geometry, and rate of growth. Two key missions, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Satellite, have played instrumental roles in refining our understanding of the CMB and the parameters of the universe. The data from these missions have allowed scientists to create the lambda cold dark matter CDM model, which includes components such as dark energy and cold dark matter. This model explains the evolution of the universe from its inception to its present state. By working backward through the CDM model, scientists estimate the universe's age at approximately 13 billion years. In addition to the CMB, astronomers also study distant objects such as galaxies and quasars to estimate the universe's age. The light from these objects, which has traveled billions of years to reach us, offers a window into the past. By observing their properties, such as their chemical composition, size, and distance, scientists can construct a timeline of cosmic evolution and further refine our estimates of the universe's age. Star clusters provide another important method for dating the universe. There are two main types of star clusters: globular clusters, which contain some of the oldest stars in the galaxy, and open clusters, which are younger. By studying the oldest stars in globular clusters, astronomers can estimate a lower limit for the universe's age. These stars, particularly low-mass ones, burn at a slower rate and have lifespans that span billions of years, providing a useful benchmark for determining how long it has been since the Big Bang. Another method employed by astronomers to date the universe involves nuclear cosmochronology. This technique involves measuring the presence of specific radioactive isotopes and their decay products in meteorites and certain types of stars. While this method is more commonly used to estimate the age of the Milky Way galaxy and its stellar populations, it also offers insights into the broader timeline of the universe, especially when combined with other observational data. Collectively, these methods form a coherent picture of the universe's age. They rely on fundamental principles of physics, including the behavior of light, gravity, and atomic processes, to paint a vivid portrait of a universe that has been evolving over billions of years. These diverse techniques converge to offer a reliable estimate of the universe's age, helping to establish a timeline that stretches back to the earliest moments of cosmic history. Observations of distant galaxies provide another crucial piece of the puzzle when it comes to understanding the universe's early expansion and overall evolution. Because light travels at a finite speed, observing distant galaxies is essentially looking back in time. By studying these galaxies, astronomers are able to observe how the universe looked billions of years ago, offering a kind of time-lapse view of cosmic history. One of the key observations that support the theory of an expanding universe comes from the redshift of light emitted by distant galaxies. This phenomenon, first observed by Edwin Hubble in the 1920s, occurs because the universe is expanding, stretching the light emitted by distant galaxies and shifting it toward the red end of the spectrum. The further away a galaxy is, the greater its redshift, which indicates that the universe is expanding uniformly in all directions. This observation formed the cornerstone of the Big Bang theory and revolutionized our understanding of the universe's origins. In addition to the expansion of the universe, more recent observations have shown that the expansion is not just ongoing, but accelerating. This discovery, which led to the identification of a mysterious force known as dark energy, has profound implications for the ultimate fate of the universe. Dark energy, which is thought to make up approximately 70% of the universe, appears to be pushing galaxies apart at an ever-increasing rate, defying the gravitational pull that should be slowing the expansion. This discovery has reshaped our understanding of the universe's dynamics and the forces that govern its evolution. Furthermore, the study of distant galaxies has revealed populations of very young galaxies, some of which were formed just a few 100 million years after the Big Bang. These young galaxies provide invaluable insights into the early processes of galaxy formation and offer clues about the conditions that prevailed in the universe's formative years. Their properties differ significantly from those of modern galaxies, providing astronomers with a direct look at the early stages of cosmic evolution. The distribution of distant galaxies across the sky also offers valuable information about the structure of the universe and its early growth. By studying these large-scale patterns, cosmologists are able to test theories of cosmic inflation, an extraordinary rapid expansion that occurred in the fractions of a second following the Big Bang. The evidence for inflation is encoded in the arrangement of galaxies and other large structures in the universe today. These observations provide critical support for the theory that the universe expanded exponentially during its earliest moments, laying the groundwork for the cosmos we see today. In summary, the study of distant galaxies, cosmic radiation, star clusters, and other astronomical phenomena has provided us with a more nuanced understanding of the universe's age, its early expansion, and its ongoing evolution. These observations continue to inform and refine our cosmological models, pushing the boundaries of knowledge and helping to piece together the grand story of the universe from its inception to its potential future. In the vastness of the cosmos, there lies an epoch so brief, so elusive, that it barely registers within the context of our understanding, the Planck epoch. This brief yet immensely significant moment occurring just after the Big Bang offers profound insights into the fundamental structure of the universe. It represents a critical point of convergence between science, theory, and mystery, providing a glimpse into the very origins of space, time, and all that we now observe in the universe. The Planck epoch is not just a footnote in the timeline of cosmic history, it is the very foundation on which everything rests. Spanning an infinitesimal fraction of a second, specifically the first 10 to the power of negative 43 seconds, this epoch is so brief that it defies human comprehension. Yet in this briefest of moments, the universe was not as we know it. It was a place of unimaginable density and temperature, where the fundamental laws of physics as we understand them today simply could not apply. The forces that govern the cosmos, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate as we perceive them now, but were unified into a single, all-encompassing force. It was during this time that the universe was compressed into a singular point, a singularity of infinite density and energy, marking the birth of everything. In fact, everything that exists today, from the smallest atoms to the largest galaxies, has its origins in this infinitesimal moment. The nature of the forces that governed the universe during this time is still one of the greatest puzzles in modern science. As we peer further back into the cosmos, we encounter a boundary, one that marks the limit of our knowledge and understanding. This boundary, the Planck epoch, lies at the intersection between classical physics and quantum theory. Beyond this point, our current theories break down, and we are left with more questions than answers. The real significance of the Planck epoch lies in its mystery and in the challenge it presents to modern science. It is the moment where classical theories of space and time cease to function, and only quantum gravity, an as yet incomplete theory, can attempt to explain the phenomena at play. For physicists, this presents a tantalizing opportunity to develop new, more powerful models of the universe that could unravel the very mechanisms that shaped its earliest moments. In the realm of cosmology, the Planck epoch plays the role of the universe's opening act. It is the precursor to everything that came after. From the very beginning, the universe began its dramatic expansion, an event known as cosmic inflation. During this period, the universe expanded exponentially in an almost inconceivably short time, from subatomic scales to the vast expanse we observe today. This rapid expansion created the conditions for the formation of galaxies, stars, and everything we see around us. Observing distant galaxies offers us a window into the past, allowing us to witness the universe's evolution from its earliest moments. Each galaxy is like a fossil, a relic of a time long gone, but still echoing in the fabric of the cosmos. Through these observations, scientists can uncover critical insights into the nature of the universe's expansion, the formation of galaxies, and the mysterious presence of dark energy, an enigmatic force that seems to drive the accelerated expansion of the universe. In this ongoing quest to understand the cosmos, one of the most promising frontiers lies in the development of more advanced telescopes and observational tools. These instruments will allow us to peer even further into the universe's past, revealing phenomena that may challenge our current theories. New observations could force us to reconsider or even abandon long-standing models of the universe's evolution, offering up fresh perspectives on cosmic inflation, the behavior of dark matter, and the nature of dark energy. Beyond these advancements in observational technology, quantum computing stands poised to revolutionize our ability to analyze the data we collect. By enabling us to process vast amounts of information more quickly and accurately, quantum computing may uncover patterns and anomalies in the cosmic microwave background radiation, faint echoes of the Big Bang, or in the large-scale distribution of galaxies. These insights could help us refine, adjust, or even overhaul existing cosmological models. In addition to these technological strides, there is the tantalizing possibility of a unified theory of physics, one that reconciles the two great pillars of modern physics, general relativity and quantum mechanics. Such a breakthrough could revolutionize our understanding of gravity, space-time, and the very conditions of the early universe, potentially providing a clearer picture of the Planck epoch and the forces that shaped it. Armed with such a unified framework, cosmologists could simulate the birth and evolution of the universe with unparalleled precision, offering answers to questions that have plagued scientists for centuries. One fascinating aspect of the early universe is the theoretical concept of primordial black holes. These hypothetical black holes are believed to have formed shortly after the Big Bang, during a period of intense density fluctuations in the infant cosmos. Unlike stellar black holes, which are born from the collapse of massive stars, primordial black holes may have arisen directly from the high-energy conditions present in the earliest moments of the universe's existence. These black holes would have formed in regions where the density of matter was so high that gravity caused space-time to collapse, creating singularities. If primordial black holes truly exist, they could serve as a unique window into the conditions of the universe's infancy. They might hold vital clues about the distribution of matter in the early universe, the behavior of gravity at extreme scales, and the elusive nature of dark matter. Some theories even propose that these primordial black holes could account for a significant portion of the universe's dark matter. If proven true, this would provide a critical piece of the puzzle regarding how galaxies formed and evolved in the first few billion years after the Big Bang. As we stand at the edge of new discoveries, both technological and theoretical, the future of cosmology looks incredibly promising. Each breakthrough, whether it's in observational technology, quantum computing, or the development of a unified theory of physics, brings us one step closer to understanding the universe's deepest mysteries. The Planck epoch, once thought to be beyond our grasp, may eventually reveal its secrets, allowing us to comprehend the origins of the cosmos in a way we can only begin to imagine. It is the story of everything that ever was and everything that ever will be. The study of primordial black holes and their interactions with their environment could unlock profound insights into the very nature of gravity and the fabric of space-time. These enigmatic cosmic objects, which are thought to have formed in the earliest moments of the universe, might serve as critical tools for testing the boundaries of Einstein's general theory of relativity. By observing how these black holes interact not only with the surrounding matter, but also with each other, we could gather empirical data that challenges and refines our understanding of gravitational forces. Their behavior could reveal new complexities within our current models, opening up fresh avenues for exploring the unseen forces that govern the universe. A particularly fascinating cosmic phenomenon, known as dark flow, has drawn the attention of astrophysicists around the world. This refers to the observed large-scale motion of galaxy clusters that appear to be moving in a specific direction across the cosmos, seemingly in a uniform stream. Discovered through meticulous observations of the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, Dark flow presents a puzzling anomaly in our understanding of the universe's behavior on the largest scales. This motion of galaxy clusters suggests a force or a structure acting beyond the observable universe, exerting influence on the matter within our own cosmos. The implications are staggering. Dark flow might point to forces originating in regions of the universe that lie beyond our observational horizon, altering the course of galaxies in ways we have yet to fully comprehend. The existence of dark flow could offer crucial support to theories proposing the existence of a multiverse, an idea that suggests our universe is but one of many, each governed by its own distinct set of physical laws. If this is true, dark flow might be a sign of gravitational forces leaking from other universes, pulling matter in our own universe in a particular direction. Such a concept fundamentally challenges the traditional cosmological principle, which asserts that the universe is homogeneous and isotropic, meaning it should look the same in all directions on large scales. If dark flow is confirmed, it would suggest that the universe may not be isotropic at all, but instead influenced by external universes, which could introduce the possibility of an underlying preferred direction in cosmic space. Another exciting avenue where dark flow might have an impact is in understanding the period of cosmic inflation. Inflation refers to a brief but extraordinary expansion of the universe that occurred within the first fraction of a second after the Big Bang. If the initial conditions of inflation were not perfectly uniform, variations in the distribution of energy and matter could have emerged, leading to the phenomenon of dark flow. Such a realization could significantly refine our understanding of inflation, offering a more nuanced and intricate view of the universe's explosive beginnings, potentially shedding light on how the cosmos was shaped during its infancy. Equally revolutionary in its own right, gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity, has become a cornerstone tool in modern cosmology. Gravitational lensing occurs when light from distant galaxies passes near massive objects, such as other galaxies or galaxy clusters. The immense gravitational field of these objects warps spacetime, bending the path of light that passes through it. This bending results in magnified, distorted, or even multiple images of distant galaxies, providing astronomers with invaluable data about the nature of the intervening mass and the large-scale structure of the universe itself. Through gravitational lensing, we gain an unprecedented ability to observe otherwise invisible phenomena, such as dark matter, which does not emit, absorb, or reflect light, making it imperceptible to traditional telescopes. By studying how light is distorted as it passes through the gravitational fields of massive objects, astronomers can infer the presence and distribution of dark matter, offering a key piece of the puzzle in understanding the elusive nature of this mysterious substance. These observations are crucial for refining our understanding of the universe's overall structure, especially its expansion. By measuring how light bends around massive clusters, scientists can determine the rate at which the universe is expanding and assess the influence of dark energy, an enigmatic force that is causing the acceleration of this expansion. Gravitational lensing also plays a pivotal role in uncovering distant, faint galaxies that were previously undetectable. These observations provide a rare glimpse into the early epochs of the universe, helping astronomers piece together the story of galaxy formation and evolution over cosmic time. This newfound ability to peer into the distant past offers an invaluable opportunity to examine the formation of the first galaxies, adding crucial data to our understanding of how structure in the universe has evolved over billions of years. The findings from gravitational lensing seamlessly integrate with broader theories of structure formation, offering new layers of insight into the universe's intricate and complex architecture. In the quest to understand the universe's origins, theoretical physicists work tirelessly to weave together the disciplines of mathematics, observation, and imaginative speculation. Their goal is to construct a cohesive framework that explains the universe's earliest moments. Central to this effort is the Big Bang theory, which posits that the universe began as an extraordinarily hot and dense point about 13.8 billion years ago. Since then, it has been expanding, giving rise to the cosmos we observe today. To model these initial conditional conditions and the subsequent evolution of the universe, physicists rely on equations derived from Einstein's general theory of relativity, often coupled with principles of quantum mechanics, though fully reconciling these two frameworks remains one of the greatest challenges in modern physics. Cosmic inflation, another critical component of these theoretical models, proposes that the universe underwent an incredibly rapid expansion in the moments immediately following the Big Bang. This theory helps explain several puzzling observations, such as the large-scale uniformity of the universe and the origin of the minute fluctuations that would eventually lead to the formation of galaxies. The validity of inflationary models is tested by studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. Precise measurements of the temperature fluctuations in this radiation, obtained through satellite observations, provide essential data to refine our understanding of the universe's earliest moments and the forces that shaped it. Each of these phenomena, whether dark flow, gravitational lensing, or the study of primordial black holes, contributes to a larger tapestry of cosmic inquiry. Together, they challenge our current understanding and inspire new theories, driving our search for the answers to some of the most profound questions about the nature of the universe and our place within it. The universe is a vast, mysterious entity, and understanding its structure and evolution is an endeavor that has intrigued physicists for centuries. The core of this cosmic puzzle lies in the enigmatic substances that make up the majority of the universe's mass energy content: dark matter and dark energy. Together, these two elusive components constitute approximately 95% of everything that exists. Yet, despite their overwhelming presence, we are still struggling to understand their true nature. To uncover the secrets of the cosmos, researchers rely on a blend of theoretical models, simulations, and astronomical observations. They delve deep into the realm of dark matter and dark energy to better grasp how these invisible forces shape the universe's expansion, its rate of growth, and its large-scale structure. However, while much of this work is grounded in mathematical and computational approaches, the actual workings of dark matter and dark energy remain largely speculative. Among the most ambitious and speculative ideas that have emerged in recent years are two fundamental theories: string theory and loop quantum gravity. Both present bold attempts to unify gravity with the other fundamental forces of nature, forces that until now have remained separate in the standard model of physics. These theories offer a tantalizing glimpse into a deeper, more fundamental description of the universe, one that might provide answers not only about how the universe behaves today, but also how it existed at its very inception, before the Big Bang. String theory, for instance, is a revolutionary framework that challenges our traditional understanding of the universe. At the heart of string theory is the notion that the universe is not made up of point-like particles, as we once believed, but rather one-dimensional strings. These strings vibrate at different frequencies, with each vibration corresponding to a different particle. This insight radically alters our understanding of matter and energy, suggesting that everything we observe is the result of these vibrating strings. But string theory goes even further. It proposes that our three-dimensional universe may be just one of many such brains, short for membranes, floating within a higher dimensional space. These brains could possess additional dimensions beyond the three spatial ones we perceive. In this context, our entire universe might be confined to one of these brains, with other brains potentially hosting other universes, each with its own set of physical laws. This theory opens up the radical possibility that the universe, in fact, may not be alone. Instead, it could be part of a larger multiverse, where multiple, possibly infinite universes exist side by side, each with its own distinct characteristics and governing principles. In string theory, the concept of the vacuum, often seen as the nothingness or emptiness of space, undergoes a dramatic transformation. Rather than being an empty void, the vacuum is understood as a seething ocean of energy, vibrating strings, and higher dimensional brains. This dynamic and complex landscape challenges the classical idea of nothing, revealing that even the most apparently empty space is teeming with quantum fluctuations, giving rise to new particles and phenomena. The vacuum, in this sense, is far from empty. It is a fertile ground for the birth of new realities. One of the most fascinating aspects of string theory is how it reimagines the origins of the universe. It suggests that the Big Bang might not have been the beginning of everything, but rather a transition, a point where the fabric of space-time as we know it emerged from an even deeper, pre-existing structure. Perhaps the seeds of the universe itself were hidden within the vacuum, where quantum fluctuations triggered the birth of our cosmos. In this scenario, the very nothing that we once believed preceded the Big Bang could have been the source of all that exists. On a similar note, loop quantum gravity, another promising theory, seeks to unify the principles of quantum mechanics with Einstein's theory of general relativity, thereby providing a coherent quantum theory of gravity. This theory challenges our perception of space-time itself, suggesting that the fabric of the universe is not continuous but rather discrete, composed of tiny, indivisible units. This view opens up new possibilities for understanding the nature of gravity, space, and time, and may offer crucial insights into the universe's origins, including the period preceding the Big Bang. Both string theory and loop quantum gravity aim to describe the universe at its most fundamental level, incorporating quantum mechanics into the very fabric of space-time. Together, they represent cutting-edge efforts to uncover the deepest truths about the cosmos and unify the fundamental forces that govern it. The implications of these theories extend far beyond the realms of abstract physics. They challenge our understanding of the universe itself, suggesting that the cosmos might not be as simple as we once thought. Instead of a static, predictable reality governed by immutable laws, the universe may be a dynamic, ever-evolving entity shaped by forces and dimensions beyond our current comprehension. One particularly mind-boggling idea that emerges from string theory and related cosmological models is the concept of the multiverse. The multiverse theory proposes that our universe is not a unique entity, but rather one of many, perhaps an infinite number, of universes that together form a vast cosmic ensemble. Each universe in the multiverse could have different physical constants, laws of nature, and even dimensions, leading to radically different forms of existence. This theory is not just a speculative fantasy. It arises from attempts to reconcile quantum mechanics with general relativity, as well as from the predictions of inflationary cosmology. According to the multiverse theory, the origins of our universe and others can be traced back to a state of nothing, that is, in fact, a quantum vacuum filled with virtual particles and energy fluctuations. This quantum foam, driven by the principles of quantum mechanics, could be the source of not just our own universe, but of an endless number of others. The idea is that our universe could have budded off from this sea of quantum fluctuations, emerging from the greater cosmic fabric as a unique bubble, complete with its own set of physical laws. Inflationary cosmology, a key part of the multiverse framework, proposes that the early universe underwent an exponential expansion, stretching rapidly in a fraction of a second. This rapid inflation could have produced not just our observable universe, but potentially infinite bubbles, each expanding into its own universe with distinct characteristics. This concept offers a tantalizing solution to some of the deepest questions about the origins of the cosmos, and suggests that the Big Bang might not have been the beginning of everything, but just one event in an ongoing process of cosmic creation. Together, these theories, string theory, loop quantum gravity, and the multiverse, are rewriting our understanding of the cosmos. They suggest that the universe, as we know it, may be just one chapter in a much larger, far more complex story. Whether or not these bold ideas will be proven correct in the future remains to be seen, but they undoubtedly represent some of the most exciting and transformative concepts in modern physics. As we continue to explore the mysteries of dark matter, dark energy, and the very fabric of space-time itself, we inch closer to unveiling the hidden truths that govern the universe. And perhaps one day, we will discover that the universe is not a solitary existence, but part of a vast, interconnected multiverse where anything and everything is possible. In recent years, string theory has introduced an intriguing and complex concept, the idea of a vast landscape of possible vacuum states. Each of these states corresponds to a unique configuration of string vibrations and brane arrangements, where transitions between these vacuums may catalyze the birth of entirely new universes. This notion opens up the possibility that universes could emerge spontaneously from what seems to be nothing. Yet this nothingness, when viewed through the lens of quantum physics, is anything but empty. Instead, it teems with latent potential, brimming with the possibility of creating entire universes. This revolutionary idea forces us to reconsider our understanding of causality and existence. Traditionally, we have thought of causality in terms of a linear cause and effect sequence, every effect having a preceding cause. But if the universe can spontaneously come into existence from a vacuum state without an obvious cause, this challenges the foundations of classical physics. It raises profound questions about the sufficiency of naturalistic explanations and whether the universe might require a cause that lies outside the conventional boundaries of natural science. If the quantum vacuum can give rise to entire universes, perhaps the laws of physics themselves can allow for such cosmic births under the right conditions. Moreover, this mind-bending concept not only reshapes our understanding of the origins of our universe, but also influences how we conceptualize the larger cosmos. It invites us to think about the universe as just one of many that could exist within a much broader and potentially infinite multiverse. The implications of this are far-reaching, with significant philosophical consequences about the nature of reality, existence, and the very structure of the universe itself. At the heart of this discussion lies the notion of nothingness. In traditional philosophical and metaphysical terms, nothing signifies the absolute absence of anything. No properties, no potential, no energy, no form. It is a void, an emptiness, devoid of meaning or substance. However, when we turn to modern physics, particularly those theories that explore the origins of the universe from quantum fluctuations within a vacuum, we are forced to reconsider what nothing truly means. Far from being an empty, meaningless void, the quantum vacuum emerges as a state brimming with possibilities, a realm where particles can spontaneously appear and disappear in a whirlwind of energy fluctuations. This redefinition of nothingness upends traditional views of causality and existence. The classical view suggests that for something to come into being, it must have a cause, a preceding event or condition. However, the idea that a universe can emerge from a quantum vacuum without a preceding cause calls this assumption into question. Could it be that the universe exists simply because it is the natural outcome of the inherent potential within a quantum vacuum? This suggests that perhaps existence itself is a more natural and fundamental state than we once thought. The idea that something can emerge from nothing forces us to reconsider why there is something at all, rather than nothing, a central and age-old question in metaphysics. In this new framework, existence itself becomes something worth exploring. What if the universe does not need a divine creator or a prime mover, as many traditional philosophical and theological arguments have suggested? If the universe can arise naturally from a vacuum, then perhaps it is not so surprising that it exists. This could lead to a reevaluation of long-held beliefs about the need for a creator, with science, philosophy, and theology engaging in a new dialogue about the origins of the universe and the fundamental laws that govern its existence. Furthermore, the idea of a universe emerging from nothing raises fascinating philosophical questions about the nature of nothingness itself. If nothingness is not truly an absence, but a state filled with potential energy and quantum fluctuations, then our entire understanding of non-existence must be rewritten. Could it be that what we have always considered nothing is merely a temporary state, a point in a continuum of potential realities? Philosophers and physicists alike might be challenged to rethink the very fabric of reality as we know it. The quest to understand how a universe could emerge from such an unlikely state is not just an intellectual curiosity. It drives ongoing research in the realms of theoretical physics and cosmology. Throughout the history of science, anomalies in observed phenomena have often spurred the development of radically new theories that completely transformed our understanding of the universe. The current theoretical frameworks, such as general relativity and quantum mechanics, have proven to be highly successful in many ways, yet they show signs of their own limitations, particularly when it comes to explaining the origins of the universe itself. General relativity, for instance, breaks down at the singularity point of the Big Bang, where densities and temperatures reach infinite extremes. Meanwhile, quantum mechanics operates on a much smaller scale, where particles can appear out of the vacuum due to quantum fluctuations in energy. These two theories, while both foundational, seem incompatible when applied to the universe's origins. This discrepancy suggests that our understanding of nothingness and of the universe's creation might be incomplete, calling for new physics that can bridge the gap between these two realms. One promising area of research is the pursuit of a theory of quantum gravity, a framework that unifies quantum mechanics with general relativity. Theoretical models like loop quantum gravity and string theory seek to describe spacetime at the Planck scale, where the effects of both gravity and quantum mechanics are most pronounced. If these theories can be successfully developed, they might provide insights into how a universe could emerge from the quantum vacuum, offering a natural and scientifically grounded explanation for its origin. Such breakthroughs in our understanding of physics could revolutionize our conception of the cosmos. If the universe can indeed emerge from nothing, or from a quantum vacuum filled with energy fluctuations, it would forever alter our understanding of the laws of nature. The boundaries between what we think of as nothing and something would blur, leading to a profound shift in how we understand the very essence of existence. In this new paradigm, the line between existence and non-existence becomes far more fluid, and the universe might not be the miraculous anomaly we once thought, but rather a natural consequence of the quantum fabric of reality. This exploration of nothingness, causality, and the origins of the universe is not merely theoretical. It represents the frontier of human knowledge, where science, philosophy, and even theology converge. The implications of a universe emerging from nothing could reshape our very understanding of existence, offering a glimpse into the deeper mechanics of the cosmos, and perhaps even revealing that what we call nothing is in fact something far more extraordinary than we could have ever imagined. The exploration of dark energy and dark matter, two of the most elusive and pervasive components of the universe, holds the potential to unravel new laws of physics that could fundamentally reshape our understanding of the cosmos. Together, these entities constitute most of the mass energy content of the universe, yet they remain largely mysterious, evading direct detection despite being vital to the universe's structure and behavior. Deciphering their nature could reveal the hidden forces that shape the birth and evolution of the universe. As scientists probe these cosmic enigmas, they may unlock groundbreaking discoveries that challenge long-held beliefs and offer insight into the deepest mechanics of space and time. Recent advancements in observational technology, such as more sensitive telescopes and advanced detectors, are pushing the boundaries of our ability to observe distant corners of the universe. These tools may soon enable us to capture signals from the earliest moments of cosmic history, potentially offering empirical evidence that challenges existing theories and prompts the development of entirely new ones. For instance, the cosmic microwave background radiation, a faint echo from the Big Bang, has already provided a profound shift in our understanding of cosmology. As technology advances, future observations may reveal even more extraordinary details, such as signatures of pre-Big Bang physics, clues to a time before the universe as we know it began. Theoretical concepts, such as the manipulation of fundamental cosmological forces, currently reside within the realm of speculative science. But as the potential for these manipulations enters discussions, it raises profound ethical questions. If someday we gain the capability to alter forces like gravity or electromagnetism on a cosmic scale, it could change the very nature of the universe. While such feats are far beyond our current technological reach, their theoretical exploration brings forth ethical considerations that cannot be ignored. The Pandora's box opened by these possibilities demands careful scrutiny. The first ethical concern lies in the unintended consequences of manipulating fundamental forces. What would happen if such interventions destabilize the delicate balance of cosmic structures? Could altering the forces that govern celestial bodies disrupt their orbits or change the conditions essential for life? as we know it. Given the vast scale and irreversible impact such actions could have, the risks must be carefully weighed, much like the ethical debates surrounding other advanced technologies such as genetic engineering or artificial intelligence. In these fields, too, the potential for irreversible harm looms large. Alongside the concern of unintended consequences, the question of consent emerges when considering large-scale interventions in the cosmos. Who would have the authority to make decisions that could alter the fundamental nature of the universe, affecting countless civilizations or life forms that may exist elsewhere? This brings to the forefront the issue of cosmic stewardship and intergenerational ethics. How do we balance the desires of present generations to explore and modify the universe with the needs and rights of future beings, whether human or otherwise? These questions challenge us to reflect on our moral obligations, not just to ourselves, but to future inhabitants of the cosmos. The manipulation of cosmic forces also raises the specter of deepening inequalities. If technologies that allow the alteration of universal laws ever become a reality, who would control them? Would such power be concentrated in the hands of a few, enabling them to dominate cosmic resources or control vast territories within the universe? This creates an urgent need for frameworks of cosmic justice and governance, systems that ensure equitable access to these powers and prevent exploitation on a galactic scale. Furthermore, the ethical debate extends to the preservation of the natural cosmic heritage. Just as we value and protect the natural landscapes on Earth, there may come a time when humanity must consider the universality of cosmic preservation. The wonders of the universe, planets, stars, galaxies, and perhaps even nascent life, could come to be viewed not as resources to be exploited, but as entities worthy of protection from unnecessary human interference. This calls for a deeper philosophical reflection on humanity's place within the grand tapestry of existence, prompting questions about our role in a universe much larger and older than ourselves. At the heart of these ethical considerations lies a fundamental question: what responsibilities accompany our growing scientific and technological capabilities? If humanity were ever able to manipulate the very fabric of space-time or alter the laws that govern the universe, we would be compelled to confront the limits of our ambition and recognize the potential consequences of our actions. It is not simply a matter of what we can do, but what we should do. The contemplation of pre-Big Bang scenarios takes us into even deeper, more speculative realms of cosmological inquiry. What might have existed before the explosive birth of the universe, and what could have triggered the Big Bang? These are questions that challenge the very foundation of our understanding of the cosmos. Some theories suggest that the universe may not have been created in a singular event, but rather that it undergoes an eternal cycle of creation and destruction. This idea, known as the cyclic or oscillating universe theory, proposes that the Big Bang is merely the latest in an endless series of expansions and contractions. In this model, the universe could have previously contracted to a dense, nearly infinite point, possibly a singularity, before bouncing back and expanding once more into the universe we observe today. The cyclic model challenges the traditional view of a singular, irreversible beginning of time, and instead introduces the possibility of an infinite repeating cycle. This theory, along with other speculative models, invites us to reconsider the true origins of the universe and opens the door to entirely new ways of thinking about the cosmos, suggesting that the story of the universe is far more intricate and complex than we could have ever imagined. These pre-Big Bang concepts, while still speculative, offer fascinating glimpses into a deeper understanding of the cosmos. As our tools of exploration improve and our theories evolve, we may be on the verge of uncovering mysteries that could rewrite the very narrative of existence. The question of where the universe came from, how it began, and whether it will ever end remains one of the greatest mysteries of science, offering endless opportunities for discovery, exploration, and ethical reflection. The notion that the universe may operate in a cycle of Big Bangs followed by Big Crunches points to a profound and unsettling idea: the possibility of a timeless, eternal process where there is no singular beginning. This theory, which challenges the very foundations of traditional cosmology, paints a picture of a universe that constantly renews itself, rather than originating from a single, finite moment in time. Such a perspective dissolves the need for a concrete beginning, suggesting that the cosmos could be locked in an endless loop of creation and destruction, stretching across infinity. One particularly intriguing idea that predates the Big Bang theory is rooted in the concepts of string theory. This model proposes a strikingly different view of the universe's origins, one where our universe was not born from a singular explosive event, but rather from the collision of two or more higher dimensional branes, short for membranes. These branes exist in a higher dimensional space far beyond the three spatial dimensions and one time dimension that we experience. As these branes move through this higher dimensional expanse, they inevitably collide. When they do, the immense energy released in this cosmic impact catalyzes the creation of a new universe, essentially giving birth to a Big Bang. This model doesn't just provide a potential origin story for our universe, it also offers a framework for unifying the fundamental forces of nature through the powerful language of string theory and M theory. These theories propose that all the forces and particles in the universe arise from the vibrations of tiny strings that exist in multiple dimensions. As such, the collision of branes is not only a potential trigger for the Big Bang, but could also be the key to a deeper understanding of how the forces of gravity, electromagnetism, and nuclear interactions are fundamentally connected. Another alternative approach comes from the world of quantum cosmology, which applies the strange rules of quantum mechanics to the entire universe. In this view, the singularity, the infinitely dense point from which our universe is thought to have emerged, may not be an unavoidable feature of the Big Bang. Instead, quantum effects might prevent this infinite density from occurring altogether. Instead of collapsing into a singularity, the universe might contract to a near singular point, then bounce back, initiating a new phase of expansion. This concept, often described using frameworks like loop quantum gravity, imagines a universe where spacetime itself behaves in a way that defies classical understanding. In this scenario, spacetime is quantized, and the laws of quantum mechanics prevent the formation of a singularity. Rather than reaching infinite density, the universe undergoes a quantum bounce, a cyclic process of contraction and expansion, potentially ongoing through vast epochs of time. All these theories, whether based in quantum mechanics, string theory, or the collision of higher dimensional branes, share a common goal: to stretch our understanding of the universe's origins beyond the limits of classical Big Bang cosmology. They invite us to consider the possibility that the Big Bang was not the beginning of all things, but rather one of many beginnings that could unfold across an infinite expanse of time. By incorporating insights from some of the most advanced theoretical frameworks in physics, these models challenge our very conception of time, existence, and the nature of reality itself. Despite their speculative nature, these ideas push the boundaries of cosmological inquiry. They inspire us to reconsider our place in the universe, to look beyond the observable universe, and to probe the deepest mysteries of existence. But this journey of discovery is not without its challenges. These theories face significant technical obstacles, and many aspects remain beyond our current ability to test or observe. Nevertheless, they represent a dynamic and ever-evolving quest to understand the cosmos, a quest that refuses to be bound by our conventional assumptions about the beginning of time and space. Among the most provocative and groundbreaking concepts emerging from modern cosmology is the theory of eternal inflation. This radical idea proposes a universe in which the rapid expansion described by the inflationary model, the exponential growth of the universe during the first moments after the Big Bang, does not cease after the initial burst. Instead, inflation continues indefinitely, albeit in various regions of space. The result is the creation of countless pocket universes, each a separate bubble in a much larger, ever-expanding multiverse. In this vision, what we perceive as our universe, with its familiar laws of physics and constants, is merely one bubble in a colossal cosmic bubble bath. While inflation might have ceased in our local bubble, it continues without end in other regions of the multiverse. This picture challenges traditional cosmological models, suggesting that our Big Bang was not the singular origin of everything, but just one among countless others, each with its own set of physical laws and constants. Eternal inflation fundamentally alters our understanding of the universe's origins. It suggests that the universe we observe is just a tiny fraction of an infinite, timeless multiverse. A multiverse where new universes continually spring into existence, each governed by its own unique set of rules. Rather than being the outcome of a finely tuned set of initial conditions, the properties of our universe may simply be the result of random processes within a cosmic lottery. This challenges the very notion of fine-tuning in the laws of physics, which has been used to explain the exact conditions necessary for life as we know it to exist. In this framework, the idea of a beginning to time or space becomes more and more tenuous. Instead of thinking of the Big Bang as the start of everything, eternal inflation proposes a reality where time and space are part of an eternal, self-perpetuating process. The boundaries of the universe expand beyond the observable cosmos, allowing for the possibility of infinite, unobservable universes, each a distinct reality with its own version of existence. Moreover, eternal inflation provides a new way to consider the fine-tuning problem. Instead of positing that our universe's laws and constants were delicately set to allow for the emergence of life, eternal inflation suggests that the apparent fine-tuning is a consequence of a multiverse in which a multitude of different physical laws can exist. In this vast cosmic landscape, life may arise in a relatively small fraction of universes, while others may remain inhospitable to any form of life. Ultimately, these speculative ideas, while difficult to prove or test with current technology, offer a stunning and radical perspective on the nature of the universe and its origins. They invite us to reimagine the very structure of reality, urging us to look beyond the known universe and contemplate the infinite possibilities that might exist in the ever-expanding multiverse. Furthermore, the concept of eternal inflation intersects with, and is profoundly enhanced by, developments in string theory. In particular, the idea of a vast landscape of potential vacuum states, each leading to the formation of unique universes, each possessing distinct properties, adds significant depth to our understanding of the cosmos. This convergence of ideas from inflationary cosmology and string theory strengthens the theoretical possibility of a multiverse, expanding the boundaries of what we consider possible in the realms of both the observable and the unobservable universe. Together, they encourage us to reimagine the origins of everything we know, pushing the limits of our knowledge and our conceptualization of reality itself. At the heart of this cosmic reimagining lie the theories of quantum gravity, which seek to reconcile the two great pillars of modern physics, quantum mechanics and general relativity. These theories hold profound implications, not just for our understanding of the universe's beginnings, but for our entire framework of existence. Quantum gravity challenges the traditional narrative of the universe's origin, a narrative that has long relied on the concept of a singular Big Bang, an initial, infinitely dense point from which everything we observe today exploded into existence. One of the most striking possibilities emerging from quantum gravity is the potential elimination of the singularity. This singularity, an infinitely small, hot, and dense point, was once thought to mark the boundary of time and space itself, beyond which the laws of physics as we know them simply collapse. However, quantum gravity suggests that the universe could have had a finite size from its earliest moments, governed by quantum laws that prevent the formation of such a singularity. This radically redefines the way we view the universe's birth, suggesting that the cosmos didn't emerge from nothing. Instead, it may have always had a quantifiable, albeit incredibly small, essence, a beginning not of nothingness, but of a form of existence that is far more complex than previously imagined. Additionally, theories such as loop quantum cosmology offer models that replace the Big Bang singularity with an even more fascinating scenario, the Big Bounce. In this theory, the universe may not have had a definitive beginning at all. Instead, it may have undergone cycles of contraction and expansion, driven by quantum effects. As the universe collapses under its own gravity, it might reach a critical point where quantum forces generate a repulsive effect, leading to a cosmic bounce that kicks off a new phase of expansion. This would imply that the universe we observe today could merely be the most recent chapter in an eternal cycle of cosmic birth, death, and rebirth, defying the traditional view of a universe with a singular, unalterable beginning. In addition to changing our understanding of the universe's origins, quantum gravity also opens up new ways of thinking about the very fabric of time itself. In many traditional cosmological models, time is considered a fundamental element, something that exists independently of the universe itself. In this view is the stage upon which the drama of the cosmos unfolds, always moving forward, always unyielding. However, in a quantum gravity framework, time may be an emergent property, something that arises from more fundamental, timeless quantum laws. This would mean that the Big Bang was not the absolute start of time, but rather a transition phase in a larger, timeless quantum realm, a profound shift in how we conceive of the very nature of time and causality. Moreover, the combination of quantum phenomena and gravity opens the door to even more mind-bending possibilities, such as the existence of multiple or parallel universes. Both quantum mechanics and inflation theory suggest that the cosmos is far more expansive and varied than we have ever imagined. Quantum gravity could provide the necessary theoretical framework to support the idea of the multiverse, not just as a speculative concept, but as an intrinsic feature of the universe's most fundamental structure. This perspective challenges the long-standing notion of a unique, isolated cosmic history, suggesting instead that our universe might be just one of many, each existing in its own bubble of spacetime with its own set of physical laws. This vision of a broader cosmos, one populated with potentially infinite universes, each with its own distinct set of rules, takes us into the heart of some of the most profound questions of existence itself. To delve deeper into the enigmatic world of particle physics may soon provide us with insights into the very origins of the universe, insights that we have only just begun to explore. One of the most compelling areas of this exploration is the Higgs boson, a particle once hypothesized and now experimentally verified, which has fundamentally reshaped our understanding of mass and the way it interacts with other fundamental particles. However, the search does not end with the Higgs. Researchers are now pondering the possibility of discovering new unknown particles that might help unlock even deeper mysteries. Among the most intriguing of these is the graviton, a hypothetical particle that, if discovered, could provide the missing link between gravity and quantum mechanics. The discovery of the graviton would not only rewrite the textbooks on particle physics, but it could also offer an entirely new lens through which we could view the early universe, allowing us to peer back even further, perhaps even to moments before the Big Bang itself. As technology continues to advance, particularly with the development of particle accelerators and more sophisticated detection methods, we are entering an era where such breakthroughs may soon become a reality. This could offer us unprecedented glimpses into the nature of the cosmos. For those who have witnessed the transformation of cosmology from a speculative field to a precision science, the next great discoveries hold a particular fascination. These revelations will provide not just answers, but new perspectives on the vast and ever-expanding universe, perspectives that have long eluded humanity. The exploration of dark matter and dark energy is another crucial frontier. These mysterious forces, which together account for most of the universe's mass-energy content, lie at the heart of some of the most profound mysteries of modern cosmology. But these advanced theories extend beyond the confines of scientific inquiry, delving into the realms of philosophy and existential contemplation. They challenge not only our understanding of the universe, but also the very nature of existence itself. The multiverse theory, for instance, raises profound questions about determinism and randomness. If there are indeed countless universes, each governed by its own set of physical laws, what does that mean for the concept of destiny? Are we merely a single possibility among an endless sea of potential outcomes, where the notion of fate is rendered meaningless by the sheer diversity of universal forms? In this ever-evolving journey of cosmic discovery, we stand at the precipice of what may be a revolutionary chapter in the history of human thought, a chapter that might finally answer some of our oldest and most profound questions, while also raising new ones we have yet to even imagine. The future of cosmology holds not just the keys to the universe's past, but to its very essence and the nature of reality itself. The mysterious nature of dark matter and dark energy, the unseen yet dominant forces that together make up approximately 95% of the total mass energy content of the universe, forces us to confront a humbling and unsettling truth. Our knowledge of the cosmos is astonishingly limited. This profound realization pushes us to reflect on our existence and the place of human life and consciousness within an expanse that remains largely a mystery and perhaps even indifferent to our presence. The vastness of this unknown is not just a scientific puzzle, but a deeply existential one, urging us to ponder the significance of our existence in a universe that may be far beyond our comprehension. In the pursuit of understanding, we are reminded that our quest for cosmological knowledge extends far beyond the mere accumulation of facts. It is a journey that touches the very core of who we are, challenging us to define meaning in a cosmos whose ultimate purpose remains unclear. This inquiry into the cosmos intertwines with our relentless search for answers, pushing us to confront questions about the origins of life, the nature of consciousness, and the fundamental laws that govern everything from the smallest particle to the most expansive galaxy. One of the most intriguing concepts to emerge from cosmological speculation is the theory of a cyclic universe, an idea that suggests the universe does not have a singular origin, but instead undergoes an eternal process of expansion and contraction in a series of big bangs and big crunches. This perspective presents a radically different view of cosmological origins, challenging the conventional belief in a single, finite beginning and offering instead the possibility that the universe is in a constant cycle of rebirth, forever beginning anew. This model fundamentally alters our understanding of time and existence. If the universe is indeed cyclic, then our current universe may merely be one iteration in an endless loop of cosmic creation. Such a view forces us to reconsider what we mean by the beginning of the universe. Could it be merely a point in a timeless cycle, free from the singularity that the traditional Big Bang model proposes? If so, what implications does this have for our understanding of cosmic origins? And what does it mean for the nature of time itself? The implications of this view stretch far beyond scientific speculation. If the universe is truly eternal and cyclical, then the question of causality, of how and why things begin, takes on new dimensions. In a cyclical model, the origins of matter, energy, and even the fundamental laws of physics might not be understood as isolated events, but as recurring processes that repeat throughout infinite cycles of cosmic history. This presents a significant challenge to the way we think about the universe, as well as how we relate to it. For scientists and cosmologists, this poses an intellectual conundrum, as they must reconcile observable data rooted in the assumption of a linear, time-bound universe with a theoretical model that defies traditional ideas about time and creation. For philosophers, it offers a profound invitation to reconsider the very nature of beginnings and endings, urging us to think deeply about our place in an eternal, ever-renewing cosmos. Are we merely transient beings, or do we have a purpose in this endless cosmic narrative? As we attempt to grapple with these ideas, the concept of nonlinear time emerges, presenting a striking challenge to the conventional understanding of cosmology. In a linear framework, time flows from the past through the present and into the future. But in a nonlinear conception of time, the past, present, and future may not follow such a straightforward progression. Instead, they could intersect, overlap, or even exist simultaneously in a way that defies our usual understanding. This suggests that the origins of the universe might not be bound by a singular moment of creation, but could be influenced by future events. In essence, cause and effect could become entangled in ways that are currently unimaginable in classical physics, but are at least theoretically possible within the realms of quantum mechanics and general relativity. Such a view holds the potential to unlock some of the most profound mysteries of the cosmos, including the puzzling question of why the universe is so finely tuned for life. Rather than being the result of a random series of events, the universe's apparent precision could be the outcome of an ongoing process of self-regulation, with the laws of physics themselves evolving over time to create the conditions necessary for life. This theory has the potential to revolutionize not only our understanding of the origins of the universe, but also the very nature of time itself. It suggests that time may not be the simple linear progression we have long believed, but rather a more complex and intricate structure that governs the fabric of the cosmos in ways that are beyond our full comprehension. For those drawn to the philosophical implications of such a vision, these ideas raise fundamental questions about fate, free will, and the nature of reality. Is our future already written, dictated by the future's influence on the past? Or do we hold the power to shape the course of our universe, to write our own story within the vast cosmic narrative? This exploration of nonlinear time and its connection to cosmology not only pushes the boundaries of scientific inquiry, but also invites us to rethink our place within the universe, offering a deeply interwoven narrative of existence, causality, and destiny. The endeavor to understand the origins of the universe remains one of humanity's greatest and most ambitious intellectual pursuits. It is a journey that combines science, philosophy, and unyielding curiosity in a quest to unlock the deepest mysteries of existence. While great strides have been made in cosmology, bringing us closer to understanding the vastness of the universe and its origins, there are likely aspects of this mystery that will forever remain just beyond our reach. The limits of human cognition and the constraints imposed by our observational tools mean that our understanding is always in flux, constantly evolving as we develop new methods and theories to explore the cosmos. Each new discovery pushes us closer to the truth, but with each step forward, we uncover even more complexity, presenting new questions and challenges to our understanding. Perhaps one of the most profound unknowns in this journey lies in the nature of dark matter and dark energy, forces that together account for the vast majority of the universe's mass and energy, but remain virtually invisible to our senses. As we continue to explore and deepen our understanding of the universe, these enigmatic phenomena remain a tantalizing reminder of how much there is still to learn, hinting at the immense, unfathomable complexities that still await us in the uncharted vastness of space. Moreover, the speculative realms of string theory and the concept of the multiverse invite us into a world where reality may never fully conform to the boundaries of empirical validation. These ideas, lingering at the very edges of what we can prove, challenge our current scientific paradigms and reside firmly within the domain of theoretical possibility. As we continue this ongoing dance with the cosmos, where each step forward unravels new horizons of mystery, it becomes clear that the pursuit of understanding is not merely about finding concrete answers. Instead, it emphasizes the intrinsic beauty of exploration itself, highlighting the journey as much as the destination. At the heart of this exploration lies the universe's origins, deeply intertwined with questions about existence and purpose. These are questions that may always carry elements of mystery, serving as a humbling reminder of our smallness within the vast cosmic tapestry. They provoke us, urging us to peer deeper into the unknown and to fuel the relentless human drive to understand the unknowable. The discovery of other universes, a concept that stretches the very fabric of our current understanding and imagination, introduces profound implications for how we think about nothing. Traditionally, nothing has been regarded as a void, a mere absence of matter, energy, space, and time. This simple concept, difficult enough to grasp in its own right, becomes even more perplexing when we introduce the quantum world, where particles appear and disappear, seemingly out of nowhere. The idea that our universe might be only one of many within a vast multiverse compounds this confusion, suggesting that nothing could be much more than it seems. In fact, it may be teeming with the potential for new universes to spring forth. This shift in perspective transforms our understanding of nothing. No longer is it an empty stage devoid of substance, but rather a cosmic seedbed brimming with latent energy and infinite potential for creation. In this new view, nothing becomes a fertile ground from which universes might emerge. The implications of this are profound. If other universes exist, each possibly governed by its own set of physical laws, then nothing as we understand it could be subject to forces or principles entirely foreign to us. It becomes, in essence, a cosmic chrysalis, the dormant space where new realities are waiting to be born. Moreover, within the context of the multiverse, the very conditions that give rise to new universes could be commonplace, ordinary events rather than the rare and exceptional phenomena we once believed them to be. In this scenario, nothing may not only be a void, but a dynamic, energetic state, alive with potential. This reimagining challenges the boundaries of human cognition, inviting us to question the very nature of reality and existence. It beckons us to explore the mysteries of creation itself, urging us to reconsider the foundational principles that govern our universe and its origins. Anomalies in cosmological data have long served as intriguing puzzles that challenge the bedrock of our existing scientific theories. These irregularities compel the scientific community to reassess our most fundamental understandings of how the universe operates. When observations deviate from what prevailing models predict, these discrepancies often act as sparks that ignite innovation and lead to significant revisions in our cosmic narrative. One of the most striking examples of this occurred when the rate of expansion of the universe was found to be accelerating, a discovery first made through observations of distant supernovae. This unexpected acceleration clashed with the assumptions of existing cosmological models, eventually giving rise to the revolutionary concept of dark energy. Similarly, anomalies in the cosmic microwave background radiation, the faint afterglow of the Big Bang, have raised profound questions about the uniformity and structure of the universe. These discrepancies prompted scientists to recognize that the standard model of cosmology, though powerful, was insufficient in explaining the full complexity of the cosmos. Such anomalies do more than reveal gaps in our current knowledge. They often point toward new physics, hidden forces, or dimensions of the universe that we have yet to discover. They challenge the status quo, pushing scientists to explore beyond the familiar boundaries of conventional thought. Whether through refining existing theories or developing entirely new paradigms, these anomalies serve as a driving force behind the advancement of scientific inquiry. The relentless pursuit of answers, driven by these perplexing questions, enriches our understanding of the universe and underscores its evolving, ever-expanding nature. With each new discovery, we are reminded that the cosmos is far stranger and far more wonderful than we ever imagined. Chaos theory, with its focus on the sensitivity of systems to initial conditions and the complex, often unpredictable outcomes that follow, plays a profound role in shaping our understanding of the cosmos. This mathematical framework offers valuable insight into how the intricate structures and patterns we observe in the universe, from the distribution of galaxies to the formation of solar systems, might have originated from what initially appeared to be simple, chaotic conditions. In the moments following the Big Bang, the universe was an extraordinarily hot and dense point of energy and matter. According to chaos theory, even the smallest variations in this early state could have had enormous effects on the universe's subsequent development. This principle is often illustrated through the metaphor of a butterfly flapping its wings in one part of the world, potentially causing a tornado on the other side of the globe. The idea suggests that seemingly minor changes at the universe's inception might explain the large-scale structures and cosmic patterns that emerged over time. In this way, chaos theory provides a potential pathway from the initial uniform conditions predicted by the Big Bang to the richly diverse, clumpy, and structured universe we observe today. It offers a compelling framework for understanding how order can arise from apparent chaos, helping us make sense of the mysterious and unpredictable evolution of the cosmos. This lens not only deepens our understanding of the universe's formation, but also highlights the inherent unpredictability that has shaped the universe as we know it. The theory of chaos offers a profound lens through which we can explore the universe's inherent unpredictability. It challenges the classical notion that the universe governed by deterministic laws should be predictable at all scales. Instead, chaos theory reveals a deeper, more complex truth: that the cosmos, from its most minute particles to its grandest structures, is deeply entangled in a web of interdependent forces and reactions, all of which evolve in ways that are difficult, if not impossible, to predict over long timescales. This perspective underscores an essential truth about the universe's long-term behavior. It is fundamentally unpredictable. Since the inception of the universe itself, this intricate interplay of forces has been unfolding, too complex, too dynamic, and too sensitive to initial conditions to be fully understood or forecast. The implications are immense, stretching from our understanding of how galaxies formed billions of years ago to the ultimate fate that awaits the universe in the distant future. Chaos theory forces cosmologists to confront the limitations of predictability within such a dynamic and complex system. Bridging the gap between deterministic physical laws and the randomness that defines cosmic structures, chaos theory enriches our understanding of the universe's origins. It paints a more nuanced picture of creation, one that embraces both order and disorder, structure and randomness. This duality reflects the complexity inherent in the cosmos, offering a more profound narrative of how the universe came to be, one that does not favor a simple linear progression, but rather recognizes the chaotic dance of countless factors, each influencing the others in unpredictable ways. Among the most intriguing aspects of modern physics is the phenomenon of quantum entanglement. In this strange and counterintuitive quantum state, particles become interconnected such that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This phenomenon has profound implications for understanding the very beginning of the universe. During the early, ultra-dense stages of the cosmos, when the conditions were unimaginably hot and energetic, quantum mechanics played a pivotal role. Particles were so tightly packed together that quantum entanglement would have occurred on a scale far beyond anything we observe in today's universe. In those first moments, the universe may have been in a state of remarkable order, with particles and forces intricately interwoven in a vast quantum web. The pervasive entanglement at the dawn of time suggests a level of interconnectedness that would have shaped the subsequent development of the cosmos. This high degree of coherence might offer an explanation for the uniformity observed in the cosmic microwave background radiation, which permeates the universe today. As the universe expanded, the entangled particles maintained their correlations, providing a lasting imprint of that early interconnection. This interconnectedness in the early universe could also offer profound insights into the very fabric of spacetime. It may provide clues to understanding the unified forces of the early cosmos during a period known as the Unification epoch, when the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been merged into a single coherent force. Such a state might offer a way to reconcile two of the most fundamental theories in physics: quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the force of gravity and governs the large-scale structure of spacetime. The search for a theory that unites these two fields is one of the great challenges of modern physics. The exploration of quantum entanglement in the early universe is thus more than an academic pursuit. It holds the potential to unlock deep mysteries about the structure and laws of the universe itself. If we can better understand how the universe's fundamental forces operated in those first moments, we might begin to unravel the very foundations of reality. The quest to understand the origins of the universe is not merely a scientific endeavor. It carries profound philosophical implications. By delving into the mechanisms that sparked the birth of the cosmos, we find ourselves engaging in a deeper inquiry about existence itself. The realization that our universe may have emerged from a singularity, a point of infinite density and temperature, then expanded through processes like cosmic inflation, offers a story that is as humbling as it is awe-inspiring. This cosmic narrative highlights the interconnectedness of all phenomena in the universe. From the birth of galaxies to the formation of stars, planets, and even life, every event in the cosmos is a link in a vast unfolding chain of occurrences that stretches back billions of years. And within this expansive history, humanity is but a fleeting moment, a brief blip in the grand timeline of the universe. The understanding that we are connected to this immense, dynamic cosmos brings into sharp focus the scale of existence, forcing us to confront the vastness and complexity of the forces that govern everything we know. By examining the universe's origins, we are also confronted with a profound challenge to our anthropocentric worldview. We are no longer at the center of creation, but are instead participants in an intricate cosmic drama that spans both space and time. This realization fosters a sense of cosmic humility, encouraging us to recognize that our lives, while significant on a personal or planetary scale, are part of a much larger and far more intricate narrative. Moreover, the search for the universe's origins forces us to reconsider our role within this immense cosmos. As conscious beings, we are not mere observers. We are active participants in the unfolding story of the universe. This invites us to reflect on the meaning of life, the responsibilities we carry as stewards of our planet, and our legacy in a cosmos that dwarfs our understanding. It challenges us to think beyond our immediate concerns and to contemplate the impact we will leave on a universe that transcends our comprehension. As we continue to explore these deep cosmic questions, we are confronted with one fundamental mystery. How did the universe come to be? Is it an eternal, unchanging entity, or are there forces at play that we have yet to discover? What truly set the cosmos in motion? The answers to these questions may not be immediate, but our pursuit of understanding is a journey that will shape our future and redefine our place within this vast, unfathomable universe. Join us as we continue to explore these profound questions and share your thoughts with us. How do you think the universe began? Has it always existed, or is there more to the story than we currently understand? Let us know in the comments below and subscribe to our channel Starflux to stay updated on the latest discoveries in the world of cosmology.